On the night of July the 22nd, in the year 1867, two men sat together in the quiet of the Paris Observatory, and the city beyond the walls was dark and ordinary, and the stars above it had been named and catalogued and set into their proper places in the order of things, and the sky seemed, as it always had, a matter of settled knowledge. Charles Wolf and Wolf-Rayet had turned a telescope toward the constellation Cygnus, the great swan, arranged along the bright corridor of the Milky Way, and they had introduced into the path of starlight a glass prism, and on the screen beyond it a spectrum had opened up, a long ribbon of color from red to violet, the light of a distant star pulled apart into its separate wavelengths. They had expected to see what every stellar spectrum showed, a bright rainbow background crossed by thin dark lines, each line a wavelength of light swallowed by cooler gas in the star's outer layers, each dark notch a chemical signature written by absorption. That was the order of things. That was what stars did. The darkness of the lines was the fundamental grammar of stellar light, and it had held for every star observed since the technique was first developed. What appeared instead was something different. Not dark lines crossing the bright background, but bright lines burning above it, emission bands glowing with their own intensity where the darkness should have been. Three stars in turn, each displaying the same reversal, the same anomalous luminescence, where the spectrum's logic demanded shadow. The sight had no category, it fit no known stellar type. The two astronomers recorded what they saw with the careful neutrality of scientists confronting a fact before they have any theory to receive it, and in that careful notation, written in ink in the ordinary lamplight of the observatory, the classification of Wolf-Rayet stars began. The stars they had identified that night are still there. 3 pinpricks of light in Cygnus, designated in later catalogs as HD 191765, HD 192103, and HD 192641. They occupy the same patch of sky now as they did that July evening, unchanged to any casual eye, unchanged to any small telescope pointed their way on a clear night. What changed was the understanding of what they were, and that understanding has taken more than a century and a half to build into anything like its present form, and even now it remains a work in careful progress, each decade adding resolution to a picture that grows steadily stranger and more precise. What Wolf and Rayet had found, without knowing it in those terms, were stars at the extreme end of stellar mass, living out the final chapters of enormously accelerated lives, having shed so much of themselves that the ordinary outer layers that cover every star like a thick blanket of hydrogen were gone, peeled back by forces operating on timescales that make a human lifetime or a civilization or even the entire span of our species something too brief to measure against. The hot interior that in every ordinary star lies sealed below the surface was exposed, and the exposed interior blazed. To understand how a star arrives at that state, it is necessary to begin at the beginning of its life, which is not a quiet beginning. The most massive stars, the ones that will eventually become Wolf-Rayet objects, are born out of the densest cores of molecular clouds, regions of gas and dust, where gravity has gathered material into concentrations that collapse inward with gathering force over hundreds of thousands of years. Where the sun collected perhaps one solar mass of material in the course of its formation, these stars accumulate 20, 30, 50, 80, or more solar masses in the same basic process, and the difference in outcome is not a matter of degree, it is a difference in kind. A star of 20 or 30 solar masses begins its life on what astronomers call the main sequence, The long, stable period during which a star burns hydrogen in its core and holds itself in balance between the inward pull of its own gravity and the outward pressure of the energy released by nuclear fusion. For the Sun, that stable period lasts roughly 10 billion years. For a star 20 times the Sun's mass, the core is so much hotter and the pressure driving fusion so much more intense that the hydrogen runs out in a small fraction of that time. 2 million years, 5 million years. In the deep architecture of cosmic time, that is almost nothing. That is a barely perceptible moment. The massive star lives at a rate of expenditure so ferocious that it has effectively no future, not in any stellar sense, and the haste of its burning is written in everything about it. These massive precursors are classified as O-type stars on the standard spectral scale, which runs from the hottest and most luminous blue stars at one end down through yellow stars like the Sun to the cool red dwarfs at the other. O-type stars are the rarest and most extreme of the main sequence, so rare that within several thousand light years of the Sun, only a handful can be counted, so luminous that a single one outshines hundreds of thousands of solar masses of more ordinary stars. They are blue-white and ferociously bright, and when they form within a cloud of interstellar gas, they light up that gas across light years of space, ionizing it, setting it glowing, carving great bubbles in the molecular material around them. They are the engines of the most spectacular structures in the galaxy, the glowing nebula visible in long exposure photographs as great luminous clouds in Orion or Carina or Cygnus, and they are brief. The hydrogen in the core of a massive O-type star runs low and then runs out, and when it does, the delicate equilibrium that has held the star together begins to shift. The core contracts and heats further. The outer layers expand. The star begins to change shape and character in ways that were fixed from the moment of its formation, not by any intention, but by the specific weight of gas that fell together to make it. The outer atmosphere expands to enormous radius, and for a time the star may exist as a luminous blue variable, a swollen, brilliant, almost unstable object, hovering near the limit at which radiation pressure nearly matches the inward pull of gravity, sometimes erupting in great outbursts that fling whole solar masses of material into the space around it. Other evolutionary pathways lead through a red supergiant phase, the star swelling to hundreds of times its original radius, its surface cooling even as its interior burns hotter. In either case, what follows that transition, given sufficient initial mass, is the gradual exposure of the stellar core, the slow revelation of an interior that has been hidden all along. The mechanism behind that exposure is the stellar wind. Every star loses mass to a continuous outflow of gas from its surface, driven by radiation pressure, photons pushing outward on ions and electrons and carrying them away. For the Sun, this process is gentle enough that over its entire 10 billion year life, it will lose only a small fraction of its mass to the solar wind. For the most massive hot stars, the rate of mass loss through radiation-driven winds is incomparably greater, hundreds of millions of times greater in some cases, and sustained over the full course of a compressed and violent stellar lifetime. Year by year, over timescales of hundreds of thousands of years, the outer hydrogen envelope of a massive O-type star is eroded and carried away, layer by layer, thinning like the atmosphere of a world whose air is slowly bled into space. At some point along that slow erosion, the remaining hydrogen layer becomes too thin to sustain the star's outer character, and the deeper interior is exposed. At that point, what remains is a Wolf-Rayet star. The astronomer Peter Conti, working in the 1970s, formalize this understanding into a coherent picture of how the most massive stars transform themselves over the course of their brief lives. His proposal, which became known as the Conti process, described a sequential pathway. The massive O-type star, through the action of its own radiation-driven winds, progressively strips away its outer layers, passing through intermediate states including luminous blue variables, until the deep, hot, chemically processed interior is fully exposed. What remains at each stage depends on how much material has been removed and which of the interior layers now sits at the surface. The process does not require an external agent. It requires only mass and time and the relentless outward pressure of a star's own light. The classification system that emerged over the decades following Wolf-Rayet's discovery sorted these stripped and exposed stellar interiors into subtypes based on the chemical signatures visible in their spectra. A classification of WN indicates a spectrum dominated by helium and nitrogen, the characteristic signature of a stellar surface made of material that has been processed by hydrogen burning in the stellar core, the deep interior chemistry brought up and exposed. A classification of WN indicates a spectrum dominated by helium, carbon, and oxygen, the products of the next stage of nuclear burning, helium fusion, which runs below the hydrogen-burning shell and produces carbon and oxygen as its primary output. A rarer classification, WO, marks objects whose spectra show exceptionally strong oxygen emission, representing the most chemically evolved and deeply exposed stellar cores known, objects that have lost so much material and had so much of their interior exposed that even the oxygen-rich deeper layers of helium burning are accessible at the surface. Within each of these broad categories, there are numerical subtypes arranged by temperature, from WN, 2 at the hottest extreme, down through WN 8 or 9 at the cooler end of the nitrogen sequence, each step representing a change of tens of thousands of Kelvin across surfaces that in every case are vastly hotter than any ordinary star. The grid of subtypes is not a simple ladder of one property. It reflects simultaneous changes in temperature, in the degree of ionization of the surface gas, and in the specific mix of elements visible in the wind. It is a classification system built entirely on the reading of light, on the careful interpretation of emission lines, whose wavelengths and relative strengths encode the physics and chemistry of objects that no instrument has ever closely approached, and none ever will. The boundary condition for the formation of a Wolf-Rayet star through this single-star wind-stripping pathway is not an arbitrary number. At solar metallicity, meaning the abundance of elements heavier than helium, typical of stars in the sun's neighborhood, a star must have begun its life. With at least roughly 20 to 25 solar masses for its radiation-driven winds to be strong enough to carry away the entire hydrogen envelope within its available lifetime. Below that threshold, the winds are simply not powerful enough. They erode the outer layers, but they cannot complete the job. The hydrogen envelope survives. The star never fully exposes its hot interior before it runs out of time. The Wolf-Rayet state requires not only mass, but the specific intensity of radiation that only the most massive stars produce, the level of luminosity at which radiation pressure becomes a dominant force in the star's own evolution. That luminosity has a ceiling, or rather a limit, that the most massive stars approach and press against throughout their lives. It is the point at which the outward pressure of radiation, pushing on every square centimeter of the star's surface, would exactly balance the inward pull of gravity. Beyond that limit, a star cannot hold itself together in any stable configuration. The radiation would drive the outer layers away faster than gravity could contain them. Massive stars near the end of their hydrogen-burning lives approach that limit closely, some apparently crossing it temporarily in the great eruptive episodes of the luminous blue variable phase. It is a boundary written into the physics of radiation and gravity that the most massive stars spend their entire lives pressed against, and it is what makes their winds so powerful, and their mass loss rates so extreme, and their evolution so swift, and their final exposed interiors so hot. The three stars in Cygnus that Wolf and Rayet recorded in their notes on that July night, a century and a half ago, were pressing against that same boundary, losing mass in the same fierce winds, exposing the same processed interiors that all Wolf-Rayet stars expose. They have not changed their nature in the time since two astronomers aimed a prism at their light. They were already near the end of what was, in stellar terms, an extraordinarily brief life, and they remain what they were, burning and shedding and gradually diminishing, their hot cores blazing in the part of the spectrum that no unaided eye can see. The time between their discovery and now is not even a flicker of a moment against the lifetimes they had already lived before that July evening. To stand in the dark and look toward Cygnus on a clear summer night and know that those particular points of light are different in kind from all the thousands of others scattered across the same patch of sky, that is a quiet thing. The sky looks the same from any angle, any historical moment, any position of understanding or ignorance. The stars do not change their appearance to acknowledge what is known about them. HD 192103 sits in Cygnus and burns with its own invisible intensity, and without a prism and a careful eye, nothing in its faint pinprick of visible light suggests what it is. This is why the spectral line remains the central instrument of understanding for these objects, the one tool that can distinguish a Wolf-Rayet star from an ordinary blue star of similar apparent brightness. The specific physics of how those emission lines form is itself a window into what makes these stars so extreme. In an ordinary stellar spectrum, the lines appear in absorption because the cooler outer atmosphere of the star absorbs specific wavelengths of light passing upward from the hotter layers below. The temperature decreases outward, the outer gas is at lower temperature than the source of light behind it, and so it absorbs rather than emits. In a Wolf-Rayet star, the situation is fundamentally different. The wind flowing outward from the stellar surface is optically thick, meaning light cannot pass through it freely. The wind itself is the emitting surface, a dense outflowing plasma that radiates its own light as the gas recombines and electrons fall back into their lower energy states. The emission lines that result are broad, very broad, because the gas producing them is moving at thousands of kilometers per second, and that motion Doppler shifts the wavelengths of the emitted light both toward shorter and longer wavelengths simultaneously, spreading each line into a wide peak rather than a sharp spike. The width of those emission peaks, when displayed as a graph of brightness against wavelength, is one of the first things that makes a Wolf-Rayet spectrum recognizable. The lines are not narrow and well-defined like the features in the spectrum of a planetary nebula or the absorption lines of a normal star. They are broad, smooth hills rising above the underlying continuum, and the width of each hill is a direct measurement of the velocity of the emitting gas, a measurement of the wind itself. Every aspect of the spectrum is a physical measurement of the star's outflow, its temperature, its composition, the speed of its mass loss. The classification system built on those spectral features is not an arbitrary sorting of shapes, it is a reading of physical states. The WN subtypes, dominated by helium and nitrogen emission, carry in their chemical ratios the record of hydrogen burning by the carbon-nitrogen-oxygen cycle, the process by which hydrogen is fused to helium in the presence of carbon and nitrogen as catalysts, with the consequence that nitrogen is built up at the expense of carbon and oxygen. The star's surface, once its outer hydrogen layers have been stripped away, shows the chemical products of that deep burning, the enriched nitrogen and the depleted carbon and oxygen that are the hallmarks of CNO cycle processing. This is not a surface composition that was chosen or modified from outside. It is the interior chemistry of hydrogen fusion, now laid bare for any spectrograph aimed at the star to read. The WC subtypes show a different chemistry, carbon-rich rather than nitrogen-rich, reflecting a deeper level of exposure. In these stars, the hydrogen-burning shell and the nitrogen-enriched material above the helium-burning core have been stripped away in turn, and what the spectrograph now reads is the product of helium fusion, the triple alpha process in which 3 helium nuclei combine to form carbon, with further helium capture producing oxygen. The surface of a WC star is not a surface in any ordinary sense. It's the outflowing upper edge of a region that in other stars would be the deep interior, hundreds of thousands of kilometers below any observable surface. The carbon and oxygen that appear in the emission spectrum of a WC star were fused in the stellar core and have been gradually uncovered by the stripping of every layer that once lay above them, and they now stream outward in the wind and radiate their presence across hundreds or thousands of light years into the surrounding space. The WO subtype, rarest and most extreme, represents the final stage of this chemical exposure, the point at which even the oxygen-richest layers of the helium-burning zone have been uncovered, and the star's spectrum is dominated by exceptional oxygen emission. And WO star is showing the deepest interior accessible to observation, the most processed material in any known stellar atmosphere, the output of nuclear reactions occurring under conditions that exist nowhere else in nature outside of the cores of massive stars and the interiors of supernovae. That this can be read at all from a point of light at a distance of thousands of light years, through the analysis of the wavelengths at which the star's wind emits light, is itself a consequence of the patience and precision that stellar spectroscopy has accumulated over a century and a half of practice. Peter Conti's formalization of the evolutionary pathway in 1975 brought order to what had been a more fragmentary picture. The Conti process gave a sequential structure to the transformation. An O-type main sequence star, hot and ferociously luminous, begins to exhaust its hydrogen core. Its outer layers expand, and its radiation-driven winds grow in power. Over hundreds of thousands of years, the winds carry the hydrogen envelope away, first thinning it, then eroding it to a thin shell, then removing it entirely. Through the luminous blue variable phase, through possible red supergiant stages depending on the initial mass and metallicity, the star sheds and sheds, and at each stage what remains is slightly more exposed, slightly hotter at the surface as deeper layers come to light. The WN phase begins when the hydrogen layer is thin enough that the CNO processed material beneath is dominant in the spectrum. The WC phase follows when even the nitrogen-enriched material of the hydrogen-burning zone has been removed and the helium-burning products come to the surface. The progression is not a choice. It follows from the physics of radiation pressure, mass, and time as directly as water follows a slope. What Conti's process makes clear, in the quiet way that good scientific frameworks make things clear, is that Wolf-Rayet stars are not anomalies. They are not exceptions to the way stars work. They are the predictable outcome of the most extreme end of the stellar mass distribution, stars so massive that their own light is powerful enough to drive away their outer layers, so luminous that they exist at the edge of what gravity can contain. The strange bright emission lines that startled two astronomers in Paris on a summer night in 1867 were not signs of something outside the order of nature. They were signs of how thoroughly that order runs, extending even to the point where stars consume their own outer bodies and expose what lies within. In the years following Conti's proposal, observations of Wolf-Rayet stars in different galactic environments filled in the details of the picture. Stars in regions of higher metallicity, richer in elements heavier than helium, showed stronger winds, consistent with the idea that those metals were driving the mass loss through their interaction with radiation. Stars in lower metallicity environments, like the Magellanic Clouds, showed different properties, suggesting that the pathway from O-type star to Wolf-Rayet object depended sensitively on the chemical composition of the galaxy in which the star was born. The minimum initial mass required to become a Wolf-Rayet star through wind stripping alone was not universal. It varied with metallicity, higher in metal-poor environments where radiation pressure on heavy ions was weaker, lower in metal-rich environments where the winds were more powerful. The Conti process was revealed to be not a single fixed pathway, but a family of related pathways, whose details depended on where in the galaxy and in cosmic history the star happened to be born. Population synthesis models, which track the statistical evolution of large numbers of stars following assumed distributions of mass and metallicity, confirmed that the numbers worked. The observed rate of Wolf-Rayet stars in various galaxies was broadly consistent with the expected rate of production from the high-mass end of the stellar population, accounting for the wind-stripping pathway, and as later became clear, the additional contribution from binary star systems in which mass transfer between a pair of stars could strip the hydrogen envelope, even from stars that might not have achieved Wolf-Rayet status through single-star wind loss alone. But that is a different part of the story, and it belongs elsewhere. What matters here is the architecture of the single-star pathway, the specific mass threshold, and the radiation physics and the step-by-step removal of layer after layer that defines the Conti process and makes it the foundational framework for understanding how Wolf-Rayet stars come to be. The three stars in Cygnus have each lost many solar masses of material since they entered the Wolf-Rayet phase. That material has been carried outward in their winds and deposited in the surrounding space, sometimes sweeping into ring-shaped nebulae visible in narrow-band images, glowing in the light of recombining ions, where the fast wind has caught up with slower material ejected in earlier evolutionary phases. The gas in those nebula carries the chemical signature of the star's interior burning, enriched in nitrogen in the WN case, enriched in carbon and oxygen in the WC case, and it mixes gradually with the broader interstellar medium, altering the local chemistry of the galaxy in a small but real way. A Wolf-Rayet star does not simply burn and eventually end. It disperses itself continuously into the space around it throughout its Wolf-Rayet phase, seeding the interstellar medium with the products of nuclear fusion that no other mechanism could distribute in quite the same way. From the lamplit room in Paris, where Charles Wolf and Georges Rayet first observed those anomalous bright bands crossing the spectrum of a Cygnus star, to the present understanding of Wolf-Rayet objects as the exposed burning cores of the most massive stars in the galaxy. That distance has been crossed one observation, one theoretical refinement, one careful measurement at a time, across 157 years of accumulated work. The picture is not complete and was never claimed to be. The precise mass thresholds vary with metallicity and with binary interaction, The detailed evolutionary pathways for stars of different initial masses are still being refined. The connection between WN and WC phases is not always straightforward, and some stars may oscillate between states or pass through multiple Wolf-Rayet episodes in the course of their lives. The science is a living thing, incomplete and progressing, but the broad shape of the understanding is clear and has been clear for decades. A star forms from the densest possible birthplace in a molecular cloud. It burns its hydrogen at a furious rate. It begins to exhaust that hydrogen, and it begins to swell and shed. Its radiation presses outward against its own outer layers, with a force that increases as the luminosity approaches the Eddington limit. The outer hydrogen envelope thins and falls away in the wind, slowly at first, and then more completely, until the deep interior is exposed and the star is burning naked in space. No hydrogen mantle remaining to moderate or conceal the chemistry of its core. This is what Wolf and Rayet saw the signature of, without knowing its name or its cause, on a July night in the 19th century, aimed at 3 faint stars in the summer sky. The process has been running since long before that night. It was running when those 3 stars first formed, when their enormous initial masses guaranteed from the very first moment that they would eventually shed themselves, layer by layer, and expose their burning cores to any spectrograph that might be aimed their way. The stripping was not an accident or an aberration. It was the necessary consequence of being born so massive, so luminous, so close to the edge of what gravity can hold. The Conti process is not a mechanism imposed on these stars from outside. It is the expression of their own nature, the working out of their initial conditions through time, as unhurried and as certain as any other law written into the physics of matter and radiation. Each layer of hydrogen exhaled into the dark over hundreds of thousands of years was always going to be exhaled. Each deeper layer of nitrogen-enriched or carbon-enriched material was always going to be uncovered. The star moves inward, not toward anything it seeks, but toward what it simply and inevitably is beneath the surface, something older, hotter, more elemental, the true interior that was always there, waiting quietly beneath every outer layer the wind had not yet reached. At the surface of the hottest Wolf-Rayet stars, the temperature reaches beyond 100,000 Kelvin. The Sun, by comparison, burns at just under 6,000 Kelvin at its visible face. That gap is not simply large. It is the difference between a candle and a furnace the size of a continent, held at that heat without pause for hundreds of thousands of years. 100,000 Kelvin is a number that resists ordinary feeling, but there are ways to approach it slowly, to let it settle. At the Sun's surface, iron exists as a gas. Molecules cannot survive. Atoms themselves are stripped of their outermost electrons. At 100,000 Kelvin, atoms of oxygen lose not 1 or 2 electrons, but 3 or 4 simultaneously, and the radiation pouring from that surface lies almost entirely in a range of light the human eye cannot perceive. At wavelengths shorter than violet, in the extreme ultraviolet, where the photons carry enough energy to tear through ordinary matter, the way a stone passes through still water. The light from these stars is mostly invisible to us. It does not reach the retina. It does not register on most instruments pointed at the sky from the ground, because the atmosphere absorbs it long before it arrives. The full output of a Wolf-Rayet star, the true measure of its power, exists in a spectrum that no unaided human sense has ever directly felt. What reaches the eye in the telescope is a remnant, a fraction, a cool edge of something far larger, pouring away in every direction through the dark. To measure that true output requires a correction. Astronomers examining a Wolf-Rayet star through an optical telescope record a certain brightness, a modestly bright point, perhaps notable, but not obviously the most luminous object in the field. Then the bolometric correction is applied, a calculated adjustment that accounts for all the light at wavelengths the telescope misses, the ultraviolet and extreme ultraviolet flood pouring silently above the measurement. When the correction is complete, the star's true luminosity emerges. It is not 10 or 20 times the sun's output. It is 100,000 times, sometimes 1,000,000 times, the energy the sun releases each second. A star that looks quiet in the optical holds, in its full spectrum, one of the most powerful sustained energy outputs in the galaxy. The total range of luminosity across Wolf-Rayet stars spans from roughly 100,000 times the sun's output at the lower end in cooler and slightly less massive objects, up past 1,000,000 solar luminosities in the most extreme. These are not the outputs of burning in any chemical sense. The energy comes from nuclear fusion, deep in the stellar interior, hydrogen and helium pressed together under pressures and temperatures that dwarf even the stellar surface, and the radiation produced there works its way outward through thousands of kilometers of overlying gas before emerging. By the time it reaches the surface and begins its journey into space, it has been absorbed and re-emitted so many times that its original form is gone, transformed entirely into the continuous outward flood of photons that constitutes the star's luminosity. A law of physics governs how much energy a hot surface radiates. The energy emitted per unit area of surface scales with the fourth power of the temperature. This means that doubling the surface temperature does not double the energy output per square meter. It multiplies it by 16. A surface 10 times hotter than another radiates 10,000 times more energy per square meter. At 50,000 Kelvin, a Wolf-Rayet surface radiates roughly 1,500 times more energy per unit area than the surface of the sun. The surface is smaller than the sun in many cases, since these are not the bloated, expanded giants of other evolutionary stages, but relatively compact objects. Yet their total output overwhelms the sun by orders of magnitude, because every square meter of that surface is pouring out energy at a rate the solar surface cannot approach. The law that describes this relationship was worked out in the 19th century, from careful measurements of heat and light in laboratories far smaller than any star. The Stefan-Boltzmann law. It is a quiet, austere expression. Energy radiated per unit area equals a constant multiplied by the fourth power of temperature. The constant is small. The fourth power of temperature at these scales is not. The mathematics was assembled on Earth from furnaces and glowing wires, and it holds across every distance and every scale the universe has offered to test it. At the surface of a star, 100 times hotter than the sun, the same relationship applies, unchanged, indifferent to the extremity it is being asked to describe. The surface temperature of a Wolf-Rayet star is not a simple single thing to define. These stars do not have clean photospheres the way the sun does, a relatively sharp surface at which the gas becomes transparent and light escapes freely. Instead, they pour themselves outward in dense, fast winds so thick that the outflowing gas remains opaque, far above what would otherwise be the stellar surface. The light that escapes comes not from a solid boundary, but from a depth within the wind, where the accumulated opacity of the overlying gas finally thins enough to let radiation pass. This is the effective photosphere, and it lies sometimes thousands of kilometers above the hydrostatic core. The temperature measured there, the temperature assigned to the stellar surface, is in fact the temperature at this depth within the wind. In the hottest objects, that temperature still exceeds 100,000 Kelvin. At the cooler end of the Wolf-Rayet range, in the late subtypes of the nitrogen sequence class, surface temperatures approach 25,000 Kelvin. This is still several times hotter than the sun's surface. These stars are cooler because they are more massive, more evolved in a particular direction, or because their dense winds have pushed the effective photosphere outward into a layer where the temperature has fallen somewhat from its deep interior maximum. Even at 25,000 Kelvin, the radiation from these objects tilts strongly toward the ultraviolet, the peak of their emission lying at wavelengths shorter than the violet edge of visible light, their output dominated by photons the eye does not see. Moving up the temperature sequence through intermediate subtypes, the peak of emission shifts further and further into the ultraviolet, and the energy carried by each photon grows proportionally. At 70 or 80,000 Kelvin, the peak lies in the extreme ultraviolet. Above 100,000 Kelvin, it enters the regime of soft X-rays. The most extreme Wolf-Rayet objects approach the border between ultraviolet and X-ray emission for the bulk of their output, a regime in which the photons are energetic enough to ionize not only hydrogen, but helium, carbon, nitrogen, and oxygen in highly stripped ionic states. These are not gentle lights. They are floods of hard, energetic radiation, and the gas surrounding these stars bears the marks of what that radiation does. Hydrogen is the simplest case. A single photon with enough energy knocks the single electron free from a hydrogen atom, and the atom becomes a proton, a bare nucleus drifting in a sea of free electrons. The hydrogen surrounding a hot Wolf-Rayet star out to distances of hundreds of light years is held fully ionized by the continuous photon flood from the star at its center. Not some of it, all of it, throughout that enormous volume, every atom of hydrogen touched by the star's radiation field left with its electrons stripped away, sustained in that state by the continuous supply of fresh ionizing photons arriving every second. When an electron does recombine with a proton, it releases a photon of a specific wavelength, a red glow called hydrogen alpha emission, and the nebula around the star shines faintly with this color in images taken at the right wavelength. The glow is not the star. It is the surrounding gas made luminous by the star's invisible ultraviolet output, a faint echo in red light of energy pouring away in wavelengths, no optical image records. The rates at which the hottest Wolf-Rayet stars produce ionizing photons are among the highest of any single stellar objects known. The most extreme emit on the order of 10 to the 49th or 10 to the 50th ionizing photons per second. These are numbers that resist ordinary analogy. There is no everyday object that sheds particles at these rates and means anything by the comparison. What they translate to is the ability of a single star to hold a sphere of interstellar gas, hundreds of light years across, in a permanently ionized state. The volume is vast and dark to the eye, but within it, every hydrogen atom is bare, every electron is free, and the state persists as long as the star shines. Beyond hydrogen, the ionizing photons from the hottest Wolf-Rayet stars carry enough energy to strip multiple electrons from heavier atoms. Oxygen, an atom that requires much more energy to ionize than hydrogen, is found in highly stripped states in the gas around these stars. 3 or 4 electrons removed from a single oxygen atom, states that require photons far more energetic than anything the sun produces at its surface. Neon follows a similar pattern, stripped to states that record the temperature of the radiation field around them, the way a thermometer records temperature, not by any display, but by the simple fact of their existence. These ionic states cannot form in cooler radiation fields. Their presence is proof, written in the chemistry of the surrounding gas, of the heat that produced them. The gas immediately above the stellar surface in these extreme objects is not a quiet place. Though sound carries no meaning in the near vacuum of stellar wind, the physical conditions in the inner wind zone are those of perpetual violent process. Radiation streams outward from below. Atoms in the overlying gas absorb photons, jump to excited states, emit photons in new directions, and are pushed outward by the momentum transferred in each absorption event. The gas is not simply heated, it is accelerated, pushed away from the star by the continuous pressure of light itself. The wind that results reaches velocities measured in thousands of kilometers per second and carries the temperature structure of the star outward with it. The temperature within the wind is not uniform. It does not stay at the surface value as the gas flows outward. The wind cools as it expands, following a gradient from the tens of thousands of Kelvin near the hydrostatic core down through progressively lower temperatures as the gas moves away from the heat source below it. Far from the star, in the outer coasting zone, where the wind has reached its terminal velocity and the gas simply flows outward without further acceleration, the temperature has dropped to several thousand Kelvin, low enough for the simplest molecules to form briefly in the densest clumps, low enough for certain dust grains to condense in carbon-rich winds. This gradient, from the extreme inner heat to the cooler outer reaches, creates a sequence of distinct zones within the wind. Each zone has its own temperature, its own density, its own dominant ions, and because different elements emit their spectral lines at different temperatures, each zone glows differently. Deep in the wind, near the photosphere, the gas is hot enough to sustain highly ionized species that require enormous energy to form. Further out, as the temperature falls, intermediate ions dominate. Further still, the cooler, less energetic species take over. The spectrum of a Wolf-Rayet star, with its many overlapping emission lines from multiple ionic species, is in part a record of all these zones together, each contributing its own light from its own depth within the moving wind, the whole blended into the broad and complex profile seen from a distance. These concentric zones do not have sharp boundaries. They grade into one another across gradients of temperature and density that shift continuously from the stellar core outward to the point where the wind merges into the surrounding interstellar medium. The inner zone, closest to the hydrostatic core, is the hottest and densest, and the photons that escape from this depth carry the highest energies. The outer zones are thin and cool. The boundary between wind and interstellar space is not a wall, but a slow dilution, the outflowing gas becoming indistinguishable from the surrounding medium over distances of light years. Within the wind, the density falls with distance from the star. At the base of the wind, just above the stellar surface, the density is high enough that the gas is effectively opaque, trapping and re-emitting radiation rather than letting it pass freely. This is why the effective photosphere lies within the wind rather than at the hydrostatic core. As the gas flows outward and the density drops, it becomes progressively more transparent. At some depth, the transparency reaches the point where photons can travel freely outward without being absorbed again, and this is the depth from which the radiation we observe ultimately escapes. That depth is the effective photosphere, and its temperature defines the surface temperature we measure. In the densest winds, this effective surface lies far above the hydrostatic core, and the temperature there is lower than the temperature of the core itself, by tens of thousands of Kelvin. Understanding where the effective photosphere sits requires careful modeling of the wind density velocity and opacity together. The opacity at any depth depends on the temperature and density, which depend in turn on the velocity, which depends on the radiation pressure, which depends on the opacity. Everything is coupled to everything else in a system that resists simple analogy. The models that describe Wolf-Rayet stellar atmospheres are among the most complex in astrophysics, requiring computers to iterate the coupled equations of radiation transport, wind dynamics, and atomic physics simultaneously across hundreds of depth points. The results, when compared to observed spectra, match with a precision that rewards the effort. The physical picture they reveal is one of layered, moving, glowing structure, not a surface, but a deep column of wind, each level radiating at its own temperature, the whole producing the rich spectral texture observed from Earth. One of the practical tools for estimating a Wolf-Rayet star's true luminosity from an observed brightness is the bolometric correction, a number derived from the temperature and the shape of the star's spectral energy distribution. For cool stars, the bolometric correction is modest because most of the energy falls in optical wavelengths, where ground-based telescopes work well. For Wolf-Rayet stars, the correction is large. A star at 50 or 100,000 Kelvin radiates almost none of its energy in the optical. The fraction of total luminosity that escapes in visible light is small. The bolometric correction must account for the vast unseen reservoir of ultraviolet and extreme ultraviolet light, and it does so by relying on the physics of how a hot gas radiates. The result transforms a modestly bright optical source into one of the most powerful objects in the local galaxy. Its true luminosity hidden by the simple fact that most of its light lies in a part of the spectrum the atmosphere absorbs before it reaches any ground-based instrument. Space-based observatories operating in the ultraviolet and X-ray have confirmed these large bolometric corrections directly. When a Wolf-Rayet star is observed across all wavelengths simultaneously, the energy distribution reveals the predicted peak in the far ultraviolet and confirms that the optical brightness represents only a small fraction of the total. The star that appears moderate in a visible light image is in its full spectral expression, burning with a sustained output that dwarfs the sun's by 6 orders of magnitude in the most extreme cases. That energy is real and continuous. It pours into the surrounding space every second, ionizing hydrogen hundreds of light years away, driving the stellar wind outward at a fraction of the speed of light and steadily eroding the stellar mass. The energy being radiated away must come from somewhere, and in a Wolf-Rayet star, it comes from the nuclear burning in the deep interior. The luminosity is so extreme that it begins to press against a fundamental limit. Radiation pressure, the outward push exerted by photons on the gas they pass through, acts against the inward pull of gravity that holds the star together. For ordinary stars, radiation pressure is a minor correction to the gravitational balance. For a star radiating at 1,000,000 solar luminosities, radiation pressure becomes a significant or dominant term in the force balance, and the star approaches the condition where radiation pressure matches gravity throughout. Above that balance point, the outer layers would be blown away continuously, which is precisely what happens. The extreme luminosity of Wolf-Rayet stars is in part the mechanism of their own mass loss. The radiation field so intense that it perpetually pushes the surface outward. This is not a rapid catastrophe. The loss of mass from a Wolf-Rayet star through its radiation-driven wind is a slow, continuous process, unfolding across hundreds of thousands of years. The rate at which mass departs is large by any astronomical standard, far exceeding anything the Sun produces, but spread over the lifetime of the Wolf-Rayet phase, it amounts to a modest fraction of the total stellar mass, enough to profoundly affect the star's evolution and the mass of whatever remnant it eventually leaves behind, but not enough to dismantle the star on any timescale that feels rapid from the outside. The energy budget of a Wolf-Rayet star is tight. The star radiates at near its maximum possible output, loses mass continuously to its wind, and burns through its nuclear fuel at a rate proportional to its luminosity. The more luminous the star, the faster the fuel is consumed, and the shorter the time before the core is exhausted. This is not a paradox, but a consequence of the physics. The most massive and luminous stars live for the shortest time, because the price of such extreme output is rapid fuel consumption. Wolf-Rayet stars, already the descendants of the most massive ordinary stars, burn through their helium fuel in hundreds of thousands to a few million years. By the measure of stellar lifetimes, this is brief. The heat at the surface, the luminosity, the wind, the ionization of surrounding gas, all are connected by the same chain of cause and physical consequence. A star born massive enough generates the interior pressure and temperature to fuse hydrogen, then helium, at extreme rates. The energy released works its way outward and emerges as luminosity. The luminosity drives a wind. The wind erodes the outer layers. The erosion exposes deeper, hotter material. The surface temperature rises as the outer envelope thins. The radiation becomes harder and more energetic. The ionization of the surrounding gas intensifies, and throughout, the energy output continues, pouring into the surrounding space in an invisible flood of extreme ultraviolet photons, each one carrying enough energy to remake the atoms it touches. The gas surrounding a Wolf-Rayet star, held ionized to distances of hundreds of light years, glows with the faint red light of hydrogen recombination. In a long exposure image taken through a filter tuned to that wavelength, the surrounding nebula appears as a softly luminous fog, without structure at large scales, without edges, sustained continuously from the single source at its center. The fog has been there, in one form or another, since the star first became hot enough to ionize hydrogen at large distances. The gas has been glowing since before the outermost edges of the ionized region even knew the star existed, since it takes light and the influence of light, time to travel from the star to the boundary of the ionized zone. The edge of the ionization zone is in a precise sense a record of how long the star has been producing ionizing radiation, expanding outward at the speed of light, since the moment the ultraviolet flood first began. The temperature gradient within the stellar wind, from the deep inner heat to the cool outer regions, is a kind of slow staircase descending outward from the most extreme conditions. Near the base of the wind, where the effective photosphere sits, and where the density is still high, the temperature may be 50,000 Kelvin or more. A few stellar radii out, the temperature has fallen to 20,000. Further still, to 10,000, then 5,000, then lower still in the outermost coasting regions. At each temperature, different atomic species find their preferred ionic states. At 50,000 Kelvin, helium loses both its electrons and becomes entirely bare. At 20,000, once ionized helium predominates. At 10,000, hydrogen recombines for the first time. At 5,000, neutral carbon and oxygen begin to appear. Each of these zones produces its own spectral contribution, its own pattern of emission lines, at its own specific wavelengths. The zone of bare helium emits nothing at optical wavelengths, its radiation pouring into the ultraviolet and extreme ultraviolet, invisible to the eye. The zone of once ionized helium emits strongly in the blue, green, and blue, lines that appear prominently in the spectra of these stars. Hydrogen, in the brief zone where it exists in the wind before being fully ionized again, contributes faint Balmer emission. Carbon and oxygen, in their various ionic states across the temperature gradient, produce lines spread through the blue and green and red portions of the optical spectrum. All of these contributions arrive at the telescope blended together, a composite signal from a column of moving glowing gas at many temperatures simultaneously. Disentangling which emission comes from which depth requires the atmospheric models, the coupling of temperature and density and velocity and opacity, but the broad structure of the spectrum, the presence of lines from multiple ionic states of multiple elements, is itself already a record of the temperature gradient, evidence that the light comes not from a single surface, but from a range of depth, each slightly cooler than the one below it, each adding its own voice to the total. The outermost regions of the wind, where the temperature has fallen enough for simple molecules to persist briefly in dense clumps, merge eventually with the surrounding interstellar medium that the wind has been sweeping up and compressing across thousands of years. The boundary between stellar wind and interstellar space is not fixed but moves outward continuously as the wind pushes into the surrounding material. The compressed shell at this boundary, denser and slightly warmer than the undisturbed interstellar medium, is the origin of the ring nebulae visible around some of these stars, expanding slowly outward at velocities far smaller than the wind itself. Between the fast-moving inner wind and the slow-moving swept-up shell lies a zone of shocked heated gas, the region where the fast wind collides with the slow-moving material it is overtaking. This shock-heated zone glows in X-rays, the gas having been heated by the collision to millions of Kelvin. It is one of the ways that Wolf-Rayet stars, despite their invisibility at optical wavelengths in the full sense, announce themselves across many parts of the electromagnetic spectrum simultaneously. Radio emission from the ionized wind, optical emission from the recombination zone, ultraviolet from the hotter inner wind, X-rays from the shocked intermediate zone, and somewhere at the boundary with the interstellar medium, the faint infrared glow of the compressed and cooling swept-up shell. The full picture is one of nested concentric zones of light and heat, each at a different temperature, each at a different distance from the stellar core, each contributing its own characteristic radiation to the total. The star at the center is never directly visible in the sense of having a clean, resolved surface. What reaches any telescope is the integrated radiation from this column of wind, the blended contributions of many depths and many temperatures, the spectrum a palimpsest of the full physical structure of the atmosphere. At the very center of this nested system, far below the effective photosphere, far below the depths that any spectral observation directly probes, the hydrostatic core burns at temperatures far exceeding anything the surface expresses. The core temperature of a Wolf-Rayet star, the temperature at which helium fusion occurs, is measured in hundreds of millions of Kelvin, 50 or 100 times hotter even than the surface of the hottest WN2 object. That heat is entirely invisible from outside. It emerges only as the total luminosity radiating from the effective photosphere, translated by many layers of absorption and re-emission from its nuclear origin into the photon flood. The wind releases into space. The connection between the invisible nuclear heat of the core and the equally invisible ultraviolet flood of the surface is the whole story of energy transport in a massive star. Energy generated at the center by nuclear fusion diffuses outward through radiation and convection, step by step through thousands of kilometers of overlying gas, each layer absorbing and re-emitting the radiation from below, the temperature dropping progressively from core to surface. until the last emission escapes into space. For most stars, this is the complete picture. For Wolf-Rayet stars, the outermost layers have been stripped away, and the effective photosphere sits not in a quiet envelope of cool hydrogen, but in a hot, dense wind still in motion. The energy escapes not from a still surface, but from a moving one, and the spectrum it carries is shaped by the motion of the gas as much as by its temperature. Slowly, across the wide dark surrounding these stars, the consequence of that outpouring continues without pause. Hydrogen, hundreds of light years away, holds its ionized state because the photon flood still arrives. Oxygen and neon in the surrounding gas remain in states that record the intensity of the radiation driving them. The faint red glow of recombination extends in every direction, sustained by the continuous source at its center. The whole vast illuminated volume dependent on the continued burning of a star that will one day cease. When the nuclear fuel in the interior is exhausted and the burning stops, the photon flood will cease. The ionized hydrogen will begin to recombine. The glow will fade. The stripped ionic states of oxygen and neon will acquire their electrons back, slowly, over thousands of years, as the last ionizing radiation disperses into the intergalactic dark. The record written in the chemistry of the surrounding gas will dissolve, element by element, as the temperature of the radiation field falls to nothing. But that end is still far ahead. For now, in the present tense of the star's Wolf-Rayet phase, the photon flood continues. The surface temperature holds at its extreme. The ultraviolet radiation pours invisibly into space in every direction, and the wind blows outward from that hot, dense atmosphere in concentric shells of progressively cooler, slower, more diffuse gas, each shell slightly further from the center than the last, each slightly cooler than the one inside it. The whole system a slowly expanding series of glowing rings, differentiated by temperature alone, spreading outward from a source of heat so extreme that most of its light will never be directly seen. At roughly 1% of the speed of light, the gas leaves the star, not in a gust, not in a wave, continuously, without pause for hundreds of thousands of years. A stream of ionized matter moves outward from the surface of a Wolf-Rayet star at 3,000 kilometers every second. In the span of 2 minutes, a particle carried in that stream would cross the distance from the Earth to the Moon. In a year, it would travel far enough to circle the Sun thousands of times over, and still the star behind it pours outward, steady and vast, and utterly indifferent to the loss. 3,000 kilometers per second is the upper range. Some Wolf-Rayet winds move at 1,500, some at 2,000, each rate measured not by watching the gas directly. No instrument yet built can track an individual particle across interstellar space, but by reading the light. When the star shines, some of its ultraviolet radiation passes through the outflowing gas on its way toward a distant observer. The gas absorbs certain wavelengths. Those absorbed wavelengths appear as dark troughs in the spectrum. Because the gas is moving rapidly toward the observer, those troughs are shifted to shorter wavelengths than the rest of the spectrum, pulled toward the blue by the motion of the absorbing material. The faster the wind, the further the shift. And so the speed of a stellar wind that has never been seen directly, that moves through a space no vessel has crossed, is read from the edge of a dark trough in a graph of light, from the faint blue boundary of what is missing. The lines most useful for this measurement are ultraviolet, a particular transition of carbon ions around 1,500 angstroms, a transition of nitrogen ions near 1,200 angstroms. These wavelengths lie beyond what ordinary glass optics will pass, beyond what most of the Earth's atmosphere will transmit, visible only from space. The satellites that recorded them flew decades ago, and their data, archived and reanalyzed, still anchor almost everything known about how fast these winds move. The blue edge of the absorption trough, called the P Cygni profile, after the star where the spectral shape was first clearly described, is the measurement. The velocity it encodes is real, and the velocity is extraordinary. For comparison, the wind leaving the sun is not slow in any ordinary sense. It crosses the distance between the sun and the earth in a few days, but its speed is typically 400 kilometers per second, and the mass it carries is very nearly nothing, roughly 100 trillionth of a solar mass every year, so little that after 5 billion years, the sun has lost almost no mass at all through its wind alone. A Wolf-Rayet wind is different in both dimensions, faster by factors of 4 to 8, and heavier by a margin so large the numbers need a moment to settle. A Wolf-Rayet star loses somewhere between 100,000th and 1/10,000th of a solar mass every year. In a single year, it may shed more matter than the sun will lose in its entire 10 billion year lifetime. In 1,000 years, more than the entire mass of the Earth. In 100,000 years, a duration that contains all of recorded human history, many times over, and yet represents only a small fraction of a Wolf-Rayet lifetime, a mass equivalent to several suns, may have been carried outward into the surrounding space, dispersed across a volume growing wider year by year at 3,000 kilometers per second. These numbers come from the spectra, from the brightness of emission lines, from calculations of how much gas must be present to produce the light observed. But the calculations carry a complication that took decades to fully appreciate. The wind is not smooth. It does not flow outward in a perfectly uniform shell, like water spreading from a sprinkler. Instead, it breaks into clumps, dense knots of gas, brighter than the gas around them, are embedded throughout the outflow. The regions between them are relatively empty. If the clumps are denser than average, then a wind that looks as bright as a uniform shell is actually carrying less total mass than it appears. The same amount of light can come from fewer atoms packed tighter, rather than from more atoms spread thin. When astrophysicists account for this clumping, correcting their mass loss estimates downward, the true rates may be smaller by factors of 2 or 3 than the uncorrected calculations suggest. The correction matters. It changes how much envelope can be stripped in a given time. It changes the final mass the star reaches before it dies. It changes what the remnant looks like. The clumps are not a detail. They are woven into every question about how these stars evolve and what they leave behind. The clumps themselves have never been imaged directly. No telescope has resolved the structure of a Wolf-Rayet wind on the spatial scales where clumping occurs. Their presence is inferred from the behavior of the spectral lines, the way emission features flicker and vary from night to night, the statistical properties of that variability carrying the signature of substructure moving through the wind. The clumps announce themselves only through the light they disturb, never by being seen, and yet every mass loss estimate made for these stars, every model of their evolution, every prediction about their remnants, is shaped by the reality of structures that exist only inferentially, dense filaments of plasma crossing space too small and too far away to resolve, their reality carried entirely in the noise of a spectral measurement. The force driving all of it, the clumps, the bulk outflow, the continuous 3,000 kilometer per second stream, is radiation. A Wolf-Rayet star is so luminous that the light pressing outward through its outer layers carries real momentum. When a photon is absorbed by an ion in the stellar atmosphere, that photon's momentum is transferred to the ion, nudging it very slightly away from the star. A single such event is immeasurably small. But in the atmosphere of a Wolf-Rayet star, each ion does not encounter one photon. It encounters many thousands. And the star does not have one ion. It has so many that the number is itself a kind of silence. The total momentum transferred by billions upon billions of absorption events, summed across the entire atmosphere, is enough to lift the gas off the surface and carry it outward against the star's own gravitational pull, accelerating continuously until the wind reaches its terminal velocity far out in the surrounding space. The mechanism works because the ultraviolet spectrum of a Wolf-Rayet star is crowded with absorption transitions. Atoms and ions of carbon, nitrogen, oxygen, silicon, and iron, each of them capable of absorbing photons at specific wavelengths, together present thousands of overlapping narrow windows into which the stellar radiation pours and is caught. Each captured photon pushes, each push is compounded by the next. The wind that results is not the product of any single line, any single element, any single interaction. It is a collective consequence, the cumulative momentum of a stellar radiation field, transferred piece by piece into a continuous outward flow of matter. This mechanism was formalized mathematically in the mid-1970s by three astrophysicists working through the line-driving problem in detail. The theory that resulted, known from their initials as the CAK theory, described how radiation pressure, acting through the forest of overlapping metal lines, could sustain a stellar wind against gravity and drive it to the velocities observed. It remains the foundation on which every quantitative model of these winds is built, though the computational complexity of tracking thousands of individual lines simultaneously still pushes the limits of what numerical models can handle with full precision. Iron deserves particular mention because its contribution to the driving is disproportionate. Iron has an extraordinarily complex electronic structure, with many electrons in configurations that produce large numbers of accessible transitions across a wide range of ultraviolet wavelengths. A single iron ion at the right temperature can absorb photons across hundreds of different spectral channels. In the driving zones of Wolf-Rayet winds, iron acts almost as a backbone for the whole acceleration process, not because it is the most abundant element, but because it is available at exactly the wavelengths where the stellar radiation is brightest, and because it presents so many opportunities for absorption at once. And this is where the question of metallicity enters, quietly and with deep consequences. Metallicity, in the language of stellar astrophysics, refers to the abundance of all elements heavier than hydrogen and helium. A star born in a region of space where previous generations of stars have already lived and died, and enriched the gas with carbon, oxygen, nitrogen, silicon, and iron, is a metal-rich star. A star born in the outer reaches of a galaxy, or in a galaxy that has had fewer generations of stellar life and death to enrich its gas, is metal poor. The Sun sits near the middle of the Milky Way's range. The inner galaxy is richer in metals than the Sun. The outer galaxy is poorer, and satellite galaxies like the Small Magellanic Cloud, orbiting the Milky Way at a distance, have metal abundances roughly a fifth of what the Sun carries, because the driving of Wolf-Rayet winds depends on the line opacity of metal ions. The strength of those winds depends on how many metal ions are present. A Wolf-Rayet star in the metal-poor Small Magellanic Cloud, its atmosphere carrying only a fifth the iron and carbon abundance of a Milky Way counterpart, at the same mass and temperature, cannot accelerate its wind as efficiently. The same radiation field acts on fewer absorbing ions and transfers less total momentum per unit time. The wind is slower. More critically, it carries less mass per year. By factors of 2 to 5, Mass loss rates drop as metallicity drops, and that reduction is not a small correction, it is a change of kind. In the inner Milky Way, where stars are born into gas already enriched by billions of years of stellar processing, a massive star approaching the Wolf-Rayet phase can strip its own hydrogen envelope through wind alone. The wind is strong enough, continuous enough, that over the hundreds of thousands of years available before the star's core runs out of nuclear fuel, the outer layers are gradually, systematically peeled away. What remains is the helium and carbon and oxygen core, exposed directly to space, radiating from temperatures that no hydrogen envelope would permit. In the small Magellanic Cloud, that wind is weaker, the peeling is slower. In some cases, a massive star that would lose its hydrogen envelope through wind alone at solar metallicity may arrive at the end of its life, still partly clothed, its outer layers never fully stripped, its core never fully exposed, the entire Wolf-Rayet stage abbreviated or altered. The mass of material still present at the moment the core exhausts its fuel affects what happens next. It affects the nature of the explosion, the mass of the remnant, the kind of gravitational object that remains after the star's death. A Wolf-Rayet star in one part of the galaxy and the same star born elsewhere at lower metallicity are different objects by the end of their lives, not because of anything in their initial structure, but because of the gas out of which they condensed, and the metals that gas either carried or lacked. Where a star is born shapes what it becomes. The galaxy is not uniform, and the variation in its metal abundance across its disk is printed into every massive star that forms within it. The wind carries this history outward. As it moves into the space surrounding the star, the Wolf-Rayet wind does not flow into empty darkness. A massive star does not begin its life blowing a Wolf-Rayet wind. Before it reached this phase, it spent millions of years as an ordinary main sequence star, then swelled and shed material in earlier, slower phases, a luminous blue variable losing mass in eruptions, or a red supergiant phase in which a slower, cooler, denser wind moved outward at perhaps a few tens of kilometers per second. The space surrounding the star, by the time the Wolf-Rayet wind begins to blow, is already filled with that earlier, slower material. It forms a kind of thick haze, a partial shell of gas enriched with hydrogen that drifted gently outward over the preceding evolutionary stages. When the Wolf-Rayet wind arrives, moving at 3,000 kilometers per second, it slams into that slow-moving pre-existing gas. The collision compresses both the fast wind and the older slow material into a thin, dense shell. This shell sweeps outward like a bubble wall, the fast wind pushing from behind, the swept-up older gas pressing from the front. Over time, the shell cools. It fragments slightly. Radiation from the star behind it ionizes the outer surface. The whole structure glows. The result is a ring nebula, a roughly spherical or elliptical shell of glowing gas surrounding a Wolf-Rayet star, visible at optical wavelengths as a thin arc or oval of faint luminosity enclosing empty-looking space, with the star at or near the geometric center. One of the best-studied examples lies in the constellation Cygnus. The nebula is a shell of compressed gas several light-years across, glowing in the reddish light of ionized hydrogen. The specific wavelength of light emitted when a proton and an electron recombine after the ionizing radiation from the central star has separated them. From the right vantage point, the nebula appears as an oval of luminous gas, its edges brighter, where the shell is thickest, and the line of sight through it is longest. At its center, the Wolf-Rayet star, a WN6-type object, pours its wind steadily outward, maintaining the pressure that keeps the shell expanding. The nebula spans tens of light years. It has been growing for tens of thousands of years. It will continue growing for tens of thousands more until the star at its center ends and the wind sustaining its expansion stops. The composition of such a nebula is not that of ordinary interstellar gas. It carries enrichment, higher abundances of helium and nitrogen than the surrounding medium would naturally hold, reflecting the chemistry of the material that the star shed during earlier evolutionary phases, when its interior nuclear processing had already altered its composition. The nebula is, in a sense, a record written in luminous gas. The elements it carries are the products of nuclear reactions that occurred in the deep interior of a massive star and were subsequently brought to the surface and blown outward by the wind. They glow now at a remove of light years from the star that produced them, slowly mixing with the surrounding interstellar medium, diluting, spreading, becoming part of the general chemical reservoir from which future stars and planets will form. Around some Wolf-Rayet stars, the nebulae are less organized, not a clean shell, but a more chaotic structure of arcs and filaments, shaped by variations in the earlier slow wind, by asymmetries in how material was shed, by the influence of neighboring stars, by the influence of neighboring stars, by the slow rotation of the system over tens of thousands of years. The universe does not always produce its structures neatly, but the principle is the same everywhere. The fast Wolf-Rayet wind compresses whatever came before it, and the interface between the two glows. Some of those interfaces are close enough to be studied in detail. Some are far enough that only their brightest emission reaches telescopes. Some lie in regions of the galaxy so dense with gas and dust that the optical emission is hidden, and only radio or infrared wavelengths can carry the signal through. The full census of Wolf-Rayet ring nebulae is still incomplete because some of the stars producing them are obscured by the very clouds from which they formed, their shells glowing unseen behind a curtain of dust that only the longest wavelengths of light can penetrate. The wind moves through all of it, the observed shells, the hidden ones, the chaotic filaments, and the clean arcs, and keeps moving. Beyond the ring nebula, beyond the compressed shell, the wind that has had time to slow and spread thins into something closer to the general interstellar medium. It carries atoms and ions that were once deep inside a massive star, atoms that have been through nuclear fire and emerged altered and now move outward at velocities still faster than ordinary stellar winds, seeding the surrounding space with material that did not exist in this form before the star processed it. The scale of this dispersal is worth resting on slowly. A Wolf-Rayet star 10,000 light years away, losing 10,000ths of a solar mass each year, has been doing so for perhaps 100,000 years in its current phase. The total mass dispersed is enormous by any comparison the body offers, tens of times the mass of the Earth per year, summed across a duration so long that the civilization reading the star's light today could not have begun to count it, and that material is not lost. It does not disappear into darkness. It joins the interstellar medium. It slows, cools, mixes with the surrounding gas, and eventually becomes part of the turbulent molecular clouds from which new stars condense. The atoms do not know where they came from. They do not carry any record of the stellar interior in which they were forged, no memory of the temperatures and pressures that produced them. But they carry the nuclear signature, the specific isotopic and elemental abundances that result from the processes that made them, and that signature, diluted but not erased, is eventually incorporated into the next generation of stars and planetary systems. The wind is not only a loss, it is a kind of dispersal into the future. And how much of that future a given star shapes depends, in the end, on where in the galaxy it was born. The inner Milky Way, metal-rich and dense with massive star formation, produces Wolf-Rayet stars, whose winds are powerful enough to strip the hydrogen envelope completely, to expose the deepest processed layers, to disperse those layers broadly before the star's end. A star born there loses more of itself over its lifetime than a star of the same initial mass born in the outer disk or in a metal-poor satellite galaxy. The remnant of the inner galaxy star arrives at the moment of its core's exhaustion, lighter, more stripped, its final state shaped not only by how massive it started, but by how efficiently the metal-rich ions in its wind carried away the outer layers across hundreds of thousands of years. A star born in the low metallicity outer disk, or in the small Magellanic Cloud, keeps more of its outer material. Its wind, weaker by factors of several, has not stripped as much. It arrives at the final phase with more mass still present. The remnant it leaves, the dense, collapsed object at the center of the explosion that ends it, may be more massive. The properties of that remnant ripple outward through consequences that extend far beyond the star's own lifetime. This is the quiet implication at the core of the metallicity dependence. The fate of a massive star, the mass of what it leaves behind, the energy of the explosion that produces it, the kind of compact object at the center of what remains, is not determined solely by how massive the star was when it formed. It is determined also by the metallicity of the gas from which it condensed, by how much iron and carbon and silicon that gas carried when the star first collapsed from it, billions of years after those elements were forged in an earlier stellar generation and dispersed into the interstellar medium. Two stars of identical initial mass, born at opposite ends of a metallicity gradient, one in the inner Milky Way, one in a metal-poor outer galaxy, will live different evolutionary histories and leave different remnants behind. The same mass, shaped by different chemical environments, becomes different objects. The galaxy writes its history into the stars that form within it, and those stars carry that history in the winds they shed and the remnants they leave. The winds do not know this. They move outward because radiation presses them. They slow because the surrounding gas resists them. They compress that gas into shells that glow for tens of thousands of years. They thin and spread and join the medium from which new stars will form. Along the inner rim of the Milky Way, the molecular clouds where massive stars are forming are already enriched by the winds of previous generations, already carrying, in their chemistry, the record of winds that blew before any human looked up at the night sky. In the outer disk, where the enrichment is thinner, where the winds of previous generations have contributed less, the clouds are simpler, less processed, closer in composition to the gas that formed the very first stars in the very early universe. Across that gradient, the wind's strength changes. The envelope stripping changes. The remnant mass changes. The star born into richer gas is more thoroughly dispersed during its own lifetime. The star born into poorer gas holds more of itself together until the end. And what that end looks like, quiet collapse, energetic explosion, or something more dramatic still, is shaped in part by a chemical gradient that stretches from one side of a spiral galaxy to the other, a gradient built from billions of years of stars living and dying and returning their substance to the space between them. The winds that reshape the space around a Wolf-Rayet star are, in this way, also shaped by the space around it, by the chemistry of the gas that bore the star, by the metals laid down there by every generation that came before. The star pours itself outward. What it can pour, and how fast, and how far, is already determined by the time it begins. In the outer reaches of the Milky Way's disk, where the molecular clouds are sparse and the metals thin, the winds move more slowly, carry less material outward, compress less gas into luminous shells. The ring nebulae there, if they form at all, are fainter and smaller. The stars at their centers are less thoroughly stripped. The future of those stars, written already in the composition of the gas from which they condensed, is different from the future written for stars in the crowded inner galaxy. And in the small Magellanic Cloud, where the metallicity is roughly a fifth of the sun's, the Wolf-Rayet stars that do exist show the predicted reduction in wind strength, confirming that the mechanism responsible is indeed the opacity of metal lines. Their mass loss rates, adjusted for distance and corrected for clumping, fall below those of Milky Way counterparts. Their envelopes are stripped less completely. Their winds carry the same nuclear processed material, the helium and nitrogen and carbon of their interiors, but in smaller quantities, over shorter distances, into a surrounding medium that is itself chemically simpler. The atoms still move outward at hundreds of kilometers per second. The shells still glow. The ring nebulae still expand. The dispersal still occurs. But the scale is smaller. The reach is shorter. The contribution to the surrounding medium is reduced. And the remnant at the end is more massive, more of the original star surviving the long, slow stripping to arrive intact at the moment of collapse. A metallicity 1/5 of the sun's is still not nothing. It is not the primordial gas from which the very first stars formed. That gas was almost entirely hydrogen and helium, with no metals at all. The first massive stars to form in the universe had no line-driven winds in the modern sense. Their outflows were driven by other mechanisms, or were much weaker than anything seen in the modern galaxy. They held their envelopes. They arrived at death differently. They left remnants that carry the signature of that pristine beginning. But those stars are gone now, dead within the first few 100 million years of cosmic time, and the gas they enriched became the nurseries for later generations, and those generations enriched it further. The gradient from the inner Milky Way to the small Magellanic Cloud, from metal-rich to metal-poor, is a pale echo of the gradient from the modern universe to the very early one. The physics is continuous. The same dependence of wind strength on metallicity that distinguishes the inner and outer Milky Way connects the modern galaxy to the first stellar generations. The mechanism that drives a Wolf-Rayet wind today is the same mechanism that was largely absent at the dawn of stellar life, and the consequences of its absence then are still being worked out in the masses of the compact objects that result, in the gravitational wave signals that encode the masses of merging remnants, in the steady, slow recovery of a universe enriched year by year by stellar winds and explosions. The wind carries all of this. It moves outward from the surface of a Wolf-Rayet star at a fraction of the speed of light, continuous and vast, carrying nuclear processed material into the surrounding space, compressing the older, slower gas into luminous shells that glow for tens of thousands of years, thinning eventually into the general interstellar medium, seeding it with carbon and nitrogen and oxygen that will one day be incorporated into new stars and perhaps into planets forming around them. The strength of that wind, and therefore the depth of the stripping and the mass of the remnant and the shape of what follows the star's death, depends on how many metal ions are present to absorb the outgoing photons and carry their momentum outward, and how many metal ions are present depends on where, in a galaxy with a chemical gradient stretching tens of thousands of light years, the star happened to condense from a molecular cloud billions of years ago. The location of a star's birth is not incidental to its fate, it is constitutive of it. The gas the star forms from carries the record of every generation of stellar life and death that preceded it, and that record is expressed continuously and silently in the speed and mass loss rate of the wind the star eventually blows, in the thickness of the shell the wind compresses, in the distance that shell travels before it fades, in the mass of the remnant that remains when the stripping is done and the core finally exhausts its fuel. Somewhere in the outer disk of the Milky Way, a molecular cloud carries gas that is poorer in metals than the sun. Within it, if a massive star is forming now, the future of that star is already different from the future of a star forming in the inner galaxy. The difference is quiet. It is written in the chemical composition of a cloud of gas drifting through space in a spiral arm, invisible to any ordinary observation, traceable only through careful spectroscopic measurement of emission and absorption lines in the gas. And yet it will determine, across a few million years, how much of that star survives its own wind, and what kind of object it leaves behind when the wind finally stops. The wind will blow regardless. The radiation presses outward, the ions absorb and are nudged, the cumulative momentum lifts the gas and carries it away, slower in some places, faster in others, weaker at low metallicity, stronger where the metals are abundant, but everywhere, from the hottest and most luminous Wolf-Rayet stars in the inner galaxy to the more modestly stripped objects in the outer disk and beyond, the wind moves outward, carrying the interior of a massive star into the surrounding space, shaping the medium through which future stars will form, writing the chemical history of a galaxy in glowing shells of gas that expand and thin and fade across tens of thousands of years, until what remains of the outflow has merged entirely with the interstellar medium and can no longer be distinguished from it. The star's substance is already dispersed long before the star itself is gone. The wind is not a prelude. For a Wolf-Rayet star, the wind is much of what the star's lifetime means. The slow, continuous relinquishing of one outer layer and then the next, across durations too long for any ordinary sense of time to hold, each year carrying away a mass the Earth could not match, each century adding to a shell of glowing gas that will outlast the star that made it by tens of thousands of years, expanding quietly into the dark, long after the source has fallen silent, and the light from the center has changed to something else entirely. The shell will still be there, moving outward at the speed the wind gave it, cooling slowly, thinning as it grows, and eventually it will be gone too, not destroyed, only dispersed, its atoms spread so thin across such a volume of space that the light they produce falls below any instrument's threshold, and the nebula that once glowed as a faint oval in the light of ionized hydrogen becomes indistinguishable from the medium around it, and the star it came from is a memory carried only in the compositions of gas clouds, too vast and slow to read easily. The wind leaves a mark, and the mark lasts, and in the end, the mark becomes the medium itself, quiet and continuous and part of everything that forms from it afterward. A Wolf-Rayet spectrum does not look like any other star's. Hold that image for a moment before the explanation arrives. In an ordinary stellar spectrum, a strip of light spread by a prism or a diffraction grating, the rainbow of color is interrupted by narrow dark gaps, thin absorption lines, where specific atoms in the cool outer atmosphere of the star have absorbed specific wavelengths on their way outward. The gaps are small and precise and numerous. They are the fingerprints of a relatively calm surface, of atoms sitting in a cool, thin layer above a deeper fire, absorbing quietly as the light passes through them. They have been the standard signature of starlight for as long as spectroscopy has existed. They are what astronomers expect. A Wolf-Rayet spectrum has none of that quiet where the dark absorption gaps should be. There are instead broad peaks of bright emission, rising steeply above the underlying continuum like slow hills of light. They are not narrow, they are not precise. They are wide, some of them spanning hundreds of kilometers per second of equivalent velocity in their breadth. And in the most extreme cases, a single emission feature can stretch across a range that a sharp absorption line would occupy in a tiny fraction. They rise and fall smoothly, these hills, without the jagged edges of a crowded absorption forest, and they glow distinctly against the fainter background continuum like something lit from within. To look at a Wolf-Rayet spectrum is to understand immediately, even before any explanation, that the gas producing these lines is moving. It is moving fast, in many different directions at once, toward the observer and away, and the Doppler spreading of all those different velocities is what gives each emission hill its particular width. The spectrum is the shape of a wind. The wind is not at the surface of the star in the way that an atmosphere sits above a planet. It begins at a surface defined not by rock or liquid, or even by the kind of photosphere a star like the Sun possesses, but by a specific depth inside the outflowing gas where the light can no longer travel freely outward, where the opacity of the wind itself creates the effective radiating boundary. That surface lies within the wind, suspended outward from whatever true hydrostatic core exists beneath, and it is at and above that surface that the emission lines are formed. Recombination happens there, and collisional excitation as electrons and ions meet and part and emit photons in the wavelengths particular to their species. The whole expanding volume of the wind above that surface is an emitting shell, a vast and slowly moving glowing haze, and the line widths record the range of velocities across it all. This is not an atmosphere above a star. It is the star's interior, wearing the wind as its outermost face. The two main chemical families of Wolf-Rayet stars each leave a different kind of record in that face. The first family shows helium and nitrogen at the surface, with the nitrogen in particular appearing in several prominent emission features in the blue part of the visible spectrum. These nitrogen-dominated Wolf-Rayet stars carry a chemistry that can be read directly as a record of hydrogen fusion. Deep inside the most massive stars, hydrogen does not burn simply. It burns through a cycle involving carbon, nitrogen, and oxygen as catalysts, each nucleus serving as a stepping stone in a chain of reactions that converts 4 hydrogen nuclei to 1 helium nucleus while releasing energy. In the steady running of that cycle, nitrogen accumulates. Carbon and oxygen are consumed and resynthesized, and consumed again, and over long time, the nitrogen fraction at the burning site rises far above any value found in the ordinary interstellar medium or in the atmospheres of less processed stars. That nitrogen enrichment is a chemical signature of the CNO cycle, as it is called, and it is written in the atmosphere of these stars as clearly as a notation on a page. The nitrogen lines in these stars, certain triplets and doublets in the blue-violet portion of the visible spectrum, glow with the chemistry of hydrogen burning that took place in the deep interior, perhaps millions of years before the present moment. Those reactions are long finished in the core of a star that has moved on to other fuels, but the products are here, at the surface, exposed. Every outer layer that once sealed them below has been stripped away, carried outward in the wind across hundreds of thousands of years, and what remains is the processed residue of the star's earliest and deepest nuclear history, radiating outward freely into space. The surface hydrogen fraction in these nitrogen-dominated Wolf-Rayet stars varies. Some still carry a significant hydrogen fraction, as much as 40 parts in 100 by mass, and these represent an earlier stage of stripping, objects where the outer envelope has been partially but not entirely removed. The wind has been working on them, and hydrogen remains. Others have none at all. No hydrogen lines appear in their spectra. The hydrogen layer is entirely gone, removed down to the helium and nitrogen core, and the star emits only what the CNO cycle left behind. The transition between these two states is not sharp. There is a gradation, a continuum of stripping between the star that still retains a hydrogen shroud and the one that has lost it entirely, and the spectrum records where along that continuum any given object sits. The surface of a nitrogen-rich Wolf-Rayet star, imagined as a place, is not a surface in any ordinary sense. There is no boundary where gas ends and vacuum begins. The density simply decreases outward, steeply at first, and then more gradually, and the point where the light we receive is generated is somewhere within that gradient, at a depth where the wind has become thin enough for radiation to escape, but dense enough to be emitting strongly. If it were possible to travel inward through that wind, the density and temperature would climb together, and the composition would remain dominated by helium and nitrogen all the way down to wherever the helium burning has begun or is beginning in the core. There is no hydrogen reservoir to pass through. It is gone, and the surface of this star is, in a real sense, its exposed nuclear residue. The second family carries a different record. In these stars, the strong nitrogen lines are absent or very faint, and in their place appear the signatures of carbon. Carbon emission features in the green portion of the spectrum, carbon and oxygen features scattered across the visible range, appear prominently and define the class. The chemistry they record is the product of the next stage of stellar nuclear burning. Once the hydrogen in a core is exhausted and the helium burning begins, the reaction that dominates is one in which 3 helium nuclei meet and fuse to form a single nucleus of carbon-12. The energy required for this triple meeting is formidable, and for most of stellar evolution, it proceeds slowly and steadily, building a growing carbon core as helium is consumed. Further reactions allow a helium nucleus to be captured by a carbon nucleus to form oxygen-16, so that the helium-burning core produces both carbon and oxygen in quantities that depend on temperature and density and time. The products of that burning are what appear at the surface of the carbon-dominated Wolf-Rayet stars. Carbon fractions of 20 to 40 parts in 100 by mass are common in these objects. Oxygen fractions of 5 to 10 parts in 100 are typical alongside them. These are not trace abundances. They are major constituents of the stellar surface, reflecting deep and sustained helium burning, the systematic conversion of helium into carbon and oxygen across a long portion of the stellar lifetime. A specific carbon emission line near the green portion of the visible spectrum and a pair of carbon lines in the orange-red serve as the primary spectroscopic markers of this class, and they glow with the direct chemical record of triple alpha fusion, 3 helium nuclei meeting under the temperatures and pressures of a stellar core, fusing into carbon. That carbon nucleus, rising over geological time through the layers of the star as stripping removes what lies above it, arriving finally at the surface and radiating its presence outward as a green emission line visible to a telescope across thousands of light years. The chain between the nuclear reaction and the observed spectrum is long and indirect, passing through millions of years of evolution and hundreds of thousands of years of wind-driven stripping, but the connection is real and traceable, and the spectrum is the record of it. There is a rare subset within this second family, objects in which oxygen emission is not merely present as a minor component, but appears with exceptional strength, dominating the spectrum in ways that indicate even more advanced chemical processing, even higher temperatures in the winds, even more complete exposure of deeply processed material. These represent the most chemically evolved Wolf-Rayet objects known, the endpoint of a stripping sequence that has removed not only the hydrogen envelope, but the bulk of the helium layer as well, exposing material in which carbon and oxygen are present in the highest ratios, and the wind temperature is among the highest observed in any stellar object. Their spectra are extreme versions of an already extreme category, and they exist at the outer edge of what stellar wind stripping can achieve in the lifetime of even the most massive stars. What makes these spectra remarkable is not merely what they contain, but what they reveal about where the information comes from. In most stars, the nuclear burning products remain sealed below a thick hydrogen envelope that the light cannot penetrate. The surface of the sun shows hydrogen and helium in roughly cosmic proportions, with very little of the cyano-processed nitrogen from its own core appearing at the surface, because the convective and diffusive mixing has not brought it there in significant quantity, and the thick outer layers remain intact. The interior chemistry of most stars is hidden. It can be inferred from models and from the measured luminosities and temperatures, but it cannot be read directly from the surface spectrum because the surface does not reflect the interior. Wolf-Rayet stars are the exception. In these objects, the wind has removed the concealing layers. What lies at the surface and in the wind is material that was once deep inside the star, processed by nuclear reactions that occurred when the star was younger and less stripped, and the spectrum reads that interior history directly. Each emission line in a Wolf-Rayet spectrum is a statement about a process that occurred at depth. The nitrogen lines say, hydrogen burned here through the CNO cycle. The carbon and oxygen lines say, helium burned here through the triple alpha process. The degree of hydrogen depletion says, the outer envelope has been removed to this depth. The temperature and ionization of the emission say, the wind is this hot, the radiation field this intense. Every feature carries specific information, and the spectrum as a whole is a layered record, a kind of geological section through the nuclear history of a massive star, read from the outside in. There is a particular quality to the emission peaks when they are examined, not just for position, but for shape. The width of each peak carries the wind velocity directly. Faster winds make broader peaks. As the wind speed is measured by examining how the peak broadens with velocity, the observer reads the dynamics of the outflow encoded in the spectral shape. And the strength of a peak relative to the continuum, how tall the hill rises above the background glow, carries information about the number of atoms emitting and the physical conditions in the wind. A strong, broad peak means a dense, fast wind, rich in the emitting species. A weaker peak means lower density, or lower abundance, or lower temperature in the emitting region. Every aspect of the shape is a datum about a physical condition in a place no instrument could ever visit directly. The emission peaks in Wolf-Rayet spectra do not arise from a single thin layer, the way most spectral lines form in a stellar atmosphere. They form across an extended volume, from different depths within the wind, at different distances from the star. Different species emit at different depths depending on their ionization requirements. The most highly ionized species, needing the highest temperatures and radiation fields to maintain their charge state, emit close to the star where conditions are most extreme. Less highly ionized species emit farther out where the radiation field has diluted and the temperature has fallen. The result is that a Wolf-Rayet spectrum is not a single snapshot of a single layer. It is a composite of many layers, each contributing its emission at its appropriate depth. The whole spectrum, a depth-integrated sum of a whole volume of chemically complex, rapidly moving, glowing gas. The emission from helium alone spans several series of lines across the spectrum, from the ultraviolet through the visible and into the infrared. One particularly strong helium line in the blue-green portion of the visible spectrum, the He2 line near 4,686 angstroms, is present in virtually all Wolf-Rayet spectra and serves as a primary classification anchor. Its presence confirms the helium-dominated surface composition. Its strength and the ratio of its intensity to the nearby nitrogen or carbon features are among the basic measurements used to assign a star to its subclass. This line is so reliably and prominently present that it can be detected even in crowded stellar fields, even in the spectra of distant galaxies, where individual Wolf-Rayet stars cannot be resolved, but their collective emission blends into the integrated light of the host stellar population. The blending of many Wolf-Rayet spectra into a galaxy's integrated light is a technique for counting these stars across distances where individual objects cannot be separated. A broad emission bump near the 4,686 angstrom helium line, rising above the underlying galaxy continuum, indicates the presence of a Wolf-Rayet population, and the strength of that bump gives a rough census of how many such stars the galaxy contains. Entire surveys of Wolf-Rayet populations in nearby galaxies have been conducted this way, reading the number of exposed helium cores from the integrated glow of light across millions of light years. The chemistry of individual stellar surfaces aggregating into a detectable signal at cosmological distances. Within individual stellar spectra, there is another kind of quiet evidence carried not in the lines themselves, but in their absence. A normal stellar atmosphere, if cool enough, will show absorption lines from a wide variety of atomic species, and if it is a nebula or a low-density ionized gas, it will show forbidden emission lines, transitions between atomic energy levels, that are allowed by quantum mechanics, but that proceed slowly, so slowly that in a dense gas they are interrupted before they can complete. In the tenuous gas of a planetary nebula or a warm interstellar cloud, forbidden lines are prominent and diagnostic. Forbidden oxygen lines in the blue-green and green portions of the visible spectrum, specifically near 4,959 and 5,007 angstroms, are among the brightest features in many nebular spectra and are standard tools of nebular diagnostics. These forbidden lines are entirely absent from Wolf-Rayet stellar spectra. Their absence is not a gap in knowledge or a failure of sensitivity. It is a physical consequence of the conditions in the wind. For a forbidden transition to produce a detectable photon, the atom must remain undisturbed long enough for the slow transition to complete. In a very dense gas, collisions between atoms and electrons happen so frequently that they interrupt the transition before the photon is emitted, redirecting the atom to a different state through a collision rather than through radiation. The density at which this collisional suppression becomes important is specific to each forbidden transition, and for the oxygen forbidden lines near 4,959 and 5,007 angstroms, that critical density is around 1,000,000 electrons per cubic centimeter. Above that density, the lines are suppressed. Below it, they appear. The electron density inside a Wolf-Rayet wind, at the depths where the emission lines form, is far above 1,000,000 per cubic centimeter. It is far above 10 million, and in the denser regions closer to the star, it reaches billions of electrons per cubic centimeter. Every atom that might produce a forbidden emission line is being collisionally interrupted before the transition can complete, again and again, continuously. The forbidden line has no chance to form. Its absence from the spectrum is not silence in the sense of nothing happening. It is silence produced by overwhelming activity, by so many collisions that the slow transitions are perpetually interrupted before they can speak. The surrounding nebulae that Wolf-Rayet stars sometimes inhabit tell a complementary story. The ring nebulae, blown outward by the stellar wind, expanding shells of gas now tens of light years from the star, have densities far below the critical threshold. In those nebula, forbidden oxygen lines appear prominently. The same oxygen species that is present in the stellar wind, but cannot emit forbidden radiation in that dense environment, can emit freely in the nebula, where the density has fallen low enough for the slow transitions to complete. A spectrum of the star and a spectrum of its surrounding nebula, taken side by side, show this contrast clearly. The stellar spectrum without forbidden lines, dense and broad and dominated by permitted emission. The nebular spectrum rich in forbidden lines, narrow and low density, and chemically illuminated by the radiation from the star at the center. The density gradient between the star and the nebula is written in the presence and absence of forbidden lines. To read that gradient from a spectrum, to understand that the missing lines encode a physical condition rather than a chemical absence, is to understand how much information a spectrum carries beyond what is immediately visible. The spectrum of a Wolf-Rayet star is full of this kind of layered meaning. The widths of lines carry velocities, the positions carry chemical identities, the ratios of line strengths carry temperature and density. The presence of certain lines and the absence of others together constrain the physical environment more precisely than either alone could do. A skilled reader of these spectra can reconstruct the three-dimensional structure of the wind, the temperature gradient within it, the abundances of every chemically significant species, and the history of nuclear burning that produced those species, all from a strip of light spread by a grating onto a detector. The light has been traveling, in most cases, for thousands of years. A Wolf-Rayet star in the Milky Way is typically several thousand light years away, and the spectrum recorded tonight is light that left the star before most human history had occurred. The star in that spectrum may have changed. Some Wolf-Rayet stars are thought to live in this state for only a few 100,000 years before the next transition in their evolution. The object whose chemistry is being read may have already moved on, already collapsed, already dispersed, but the light carries the record faithfully. The helium and nitrogen and carbon emission peaks holding their positions in the spectrum exactly as they were set when the photons departed, and the information arrives intact. There is a quality of patience in this, on the part of the light, if it is possible to imagine patience without a mind behind it. The photon emitted by a carbon ion in the wind of a Wolf-Rayet star, several thousand light years away, carries its specific wavelength without change or loss across that entire distance. It does not fade in wavelength. It does not spread into other colors. It arrives precisely at the wavelength it was emitted, shifted only by whatever motion the star has along the line of sight, and it lands on the detector and records itself there as a datum. The message is exact. The chemistry of a stellar interior, the temperature of a stellar wind, the velocity of outflowing gas, and the density of an expanding shell, all of it encoded in wavelength, carried across thousands of light years, arriving intact. The carbon-12 nucleus that formed in the triple alpha fusion event in the interior of a massive star, rising through thousands of kilometers of stellar structure as the outer layers were stripped away, appearing finally at the effective surface of the wind. emitting a photon at a specific wavelength, sending that photon across thousands of light years of interstellar space, depositing it on a terrestrial detector. The chain of events linking a nuclear reaction inside a star to a specific measurement in an observatory on Earth is one of the longest and most indirect chains of physical causation that science has managed to trace and understand. Each link is well understood. The physics of the fusion reaction, the dynamics of the wind stripping, the emission process, the propagation of light across vacuum, the recording of the photon, none of it requires speculation. The chain holds from one end to the other. What remains quietly open is the exact internal structure of the most evolved Wolf-Rayet objects, the precise mapping of which layer is currently exposed at the effective surface, the details of how mixing between layers modifies the surface composition at intermediate stages of stripping, and the precise rates at which the wind removes mass from different kinds of progenitor stars under different conditions. The spectra constrain these questions, but do not answer them completely. There are degeneracies. Different combinations of physical conditions can produce similar spectra, and disentangling them requires additional observations, theoretical models, and the careful comparison of many objects in the same subclass. The uncertainty is not large enough to undermine the broad picture, but it is real, and the researchers who work on these spectra know where the edges of confident interpretation lie. Those edges are part of the record, too. A spectrum is a projection of a three-dimensional, time-varying, physically complex object onto a two-dimensional measurement. Information is lost in that projection. The wind has structure that varies with angle from the stellar rotation axis. It has clumps and voids that introduce variability in the emission line strengths on timescales of hours to days. It has a history of mass loss that changes over the stellar lifetime, and the spectrum at any given moment reflects the current state of the wind rather than the entire history of what has passed through it. Reading the past from the present requires models that carry their own assumptions and uncertainties. The spectrum is precise, the interpretation is careful and well-grounded, but not complete. This is not a limitation of the method. It is the nature of reading any record that was created under conditions different from those of the reading. The light arrived perfectly. What the light describes is a physical system of genuine complexity, and that complexity resists complete reduction to any set of numbers a spectrum can carry. The remaining uncertainty is a measure of how rich the object is, not of any failure in the observation. In the deep blue part of the visible spectrum, a set of helium lines and nitrogen lines occupy a narrow wavelength range and are sometimes blended so thoroughly that separating their contributions requires careful analysis and high spectral resolution. The same narrow region also carries emission from ionized carbon in certain subclasses, and in some objects, a complex of blended features from multiple species creates a broad, structured peak that looks simple from a distance but resolves under closer examination into overlapping contributions from several different atoms emitting at nearly the same wavelength. Disentangling these blends is part of the work of stellar spectroscopy, and the techniques for doing it, fitting multiple Gaussian profiles, comparing synthetic spectra from atmospheric models to the observed data, have grown steadily more sophisticated as computing power and spectral resolution have increased together. Every improvement in spectral resolution reveals new structure. Lines that appeared to be single features in lower resolution spectra turn out to be blends. Variability that appeared to be noise turns out to be the signature of clumping in the wind or of a binary companion whose contribution modulates the emission with orbital phase. The spectra of Wolf-Rayet stars have been studied for more than a century and a half now, and they continue to yield new information as the tools applied to them become more precise. The broad shape of understanding, helium and nitrogen, or helium and carbon at the surface, fast outflowing winds producing broad emission, nuclear burning products exposed by stripping, was established decades ago and has not changed. The details of that broad picture have become richer and more textured with each generation of instruments. The emission peaks glow across the spectrum from the ultraviolet through the visible and into the near infrared, with different species strongest at different wavelengths. A Wolf-Rayet star observed from space, without the filtering effect of the atmosphere, reveals the full extent of its emission across this range, and the total energy emitted in spectral lines alone is a significant fraction of the bolometric luminosity. These stars radiate not merely as thermal emitters, pouring energy out across a smooth continuum. They have added to that continuum a structured landscape of emission, bright hills of line radiation rising above the underlying glow, each hill the signature of a specific atom, a specific ionization state, a specific temperature regime in the wind. The sky at night carries the light of these stars mixed into the general glow of the Milky Way, unremarkable to the naked eye, indistinguishable from any other faint star in a crowded field. The spectrum is what separates them. Through the prism of a spectrograph, the quiet point of light becomes something else entirely, a structured record of extreme chemistry, high velocity, deep nuclear history, and the patient emission of photons across thousands of light years of empty space. The difference between the naked eye view and the spectroscopic view is the difference between hearing a single note and hearing the full chord with all its harmonics, each harmonic named and traceable to its source. Late in the visible spectrum, toward the red end, certain oxygen emission lines appear in the most evolved subclass of these stars, their presence confirming the deep exposure of helium-burning products. In the green and yellow portions, the strong carbon lines of the carbon-dominated class glow with particular clarity in dark, stable atmospheric conditions when the seeing is good and the sky is steady. In the blue-violet range, the nitrogen and helium lines of the nitrogen-dominated class cluster together, their broad peaks overlapping and blending, the wind's velocity spread written across each one. The whole visible spectrum of a Wolf-Rayet star is occupied. There is no quiet stretch of continuum unmarked by some emission feature. Even in the regions between the strongest lines, weaker features of less abundant species or lower probability transitions contribute small elevations above the continuum, and a careful examination of any portion of the spectrum reveals that it is layered and structured all the way down to the noise floor. The noise floor itself, in the most precise modern spectra, is low enough that very faint features become detectable, and features that were once classified as absent are sometimes found to be present at low levels when observed with sufficient integration time and spectral resolution. The boundary between present and absent in spectroscopy is not a sharp line, but a function of instrumental sensitivity, and the spectra of Wolf-Rayet stars collected over decades from different telescopes at different resolutions with different detectors form a collective archive whose depth of detail continues to grow. Each observation adds to the record. Each new observation of a known object either confirms what was measured before or reveals something new, a variability, a previously undetected feature, a change in the emission strength that indicates something has changed in the wind. The wind changes. The emission changes in response. The spectrum is not a fixed document, but a sequence of measurements that together trace the star's behavior across time. Some Wolf-Rayet stars show variability in their emission line strengths and profiles on timescales of hours, reflecting the passage of wind clumps through the emitting volume. Others are more stable, but still show long-term trends as the mass loss rate evolves over thousands of years. The spectrum is a snapshot, and a collection of snapshots builds a picture of a system in slow, continuous motion. The wind always flowing, the emission always present, the nuclear history of the star always written in the light, patient and complete, arriving at the detector across thousands of light years of open space, precise in every wavelength, carrying its record quietly and without remainder through the dark. Somewhere in that spectrum, in a line whose width encodes the velocity of gas departing a star that no instrument has ever resolved into a disk, in the position of a peak whose wavelength identifies an atom whose presence at that surface records a nuclear event that occurred millions of years ago and thousands of kilometers below, in the absence of a forbidden line whose missing light encodes a density so high that slow quantum transitions cannot complete before the next collision arrives. Somewhere in all of that, the spectrum holds its meaning still, the way a mark holds meaning in stone, long after the hand that made it has gone, needing only the quiet attention of someone willing to read it slowly, in the dark, while the light continues to arrive. Two massive stars move through each other's gravity in a slow, continuous lean. They are not touching. Between them, across a distance that light would take minutes to cross, each star pulls at the outer layers of the other, and those layers respond, bulging toward the companion in a long tidal swell that never fully breaks. The nearer face of each star is not round but drawn, extended toward the partner, the way a drop of water at the end of a tap lengthens just before it falls. This is the geometry of a close binary system, two enormous bodies locked in an orbital embrace, and in the most extreme cases, the outer envelope of the larger star does not merely bulge, it spills. There is a surface in space between the two stars that defines the boundary of gravitational ownership. Inside it, on the primary star's side, matter belongs to that star. On the far side of the surface, matter belongs to the companion. The surface itself is a kind of threshold, invisible and precisely defined by the combined gravitational and centrifugal forces of the rotating system. When the larger star expands as it ages, swelling outward as massive stars do when the fuel in their cores begins to shift, its outer layers may reach that threshold and cross it. What follows is not explosive. It is slow. The outer hydrogen of the primary, the whole deep drifting ocean of its outermost atmosphere, begins to flow along the tidal bridge toward the companion, drawn by gravity in a steady, unhurried stream. The companion receives this material, it accretes, it brightens, and the primary, stripped of its outer envelope over thousands and then hundreds of thousands of years, is left with its core exposed. The hot inner layers that were once sealed beneath hydrogen now open to space, radiating their chemical signature outward in broad emission lines across interstellar distances. This is one of the two ways a Wolf-Rayet star comes to exist. Not through the slow self-stripping of a single massive body losing mass to its own radiation-driven wind across millions of years, but through the intimate mechanics of orbital companionship, one star's evolution effectively peeling the other from the outside in. The fraction of Wolf-Rayet stars that owe their exposed nature to a companion rather than to their own wind alone is not small. Population models that account for the full diversity of orbital separations and mass ratios across binary systems suggests that at least 4 in every 10 Wolf-Rayet stars in the Milky Way reached that state through binary mass transfer. The rest stripped themselves. But the boundary between the two channels is not always sharp, and in some systems both processes contributed. The stellar wind removing the outermost hydrogen over long timescales, while orbital geometry brought the companion close enough to accelerate the final phases. The result in either case is the same: a hot, luminous, chemically processed core broadcasting its interior through a fast, dense wind, moving through space, paired with or separated from a massive companion, burning what remains of its fuel toward an end that is already fixed. Where two stars orbit together and neither has yet completed this stripping, their winds meet between them. Each star blows its own outflow outward in all directions, and in the space between them, the two winds collide. The collision is not gentle. Wolf-Rayet winds move at speeds of thousands of kilometers per second, and when a wind at that velocity meets the wind of a companion moving toward it at comparable speed, the gas at the meeting point is compressed and heated violently. The temperature at the collision shock can reach tens of millions of Kelvin, and at that temperature the gas radiates in X-rays. The X-ray brightness of the colliding wind zone rises and falls as the stars move through their orbital cycle, brightening near closest approach when the wind densities are highest, fading toward a pastron when the stars are furthest apart and the winds have more space to thin before meeting. In the system WR 140, this orbital drama plays out on a timescale of just under 8 years. The Wolf-Rayet star there is of the WC7 subtype, its spectrum dominated by carbon and oxygen emission, its hydrogen envelope entirely gone, and its companion is a luminous O-type supergiant. Their orbit is long and stretched, an ellipse with an eccentricity of nearly 9/10, meaning that for most of their orbital cycle, the two stars are well separated. The winds thin, the collision zone faint, but every 8 years the orbit curves them close. Near closest approach, called periastron, the stars are separated by only a fraction of their average distance. The winds are dense and fast and driven together, and the collision zone flares in X-rays and does something else. It makes dust. Dust should not form near a Wolf-Rayet star. The radiation field is too intense, the temperature's too high, the photons too energetic. Dust grains, which are solid particles of carbon or silicate only nanometers across, are destroyed by ultraviolet photons and by thermal sputtering at temperatures far lower than those near a Wolf-Rayet surface. Yet at periastron in WR 140, when the two winds meet and cool at the collision interface, the compressed shocked gas reaches conditions where carbon-rich material can briefly condense into solid grains before the radiation has time to destroy them. The dust forms in the dense compressed shell of the wind-wind collision zone and is then carried outward by the winds into the surrounding space, expanding as a ring. Each periastron passage leaves one ring. Because the passage repeats every 8 years, the rings accumulate, concentric shells of carbonaceous dust expanding outward at wind velocities, each slightly larger than the last, the outermost representing the oldest passage and the innermost the most recent. In 2022, the James Webb Space Telescope turned its infrared sensitivity to WR 140 and resolved 17 of these rings directly. 17 individual arcs of condensed carbon, each one the record of a single close approach, each one moving silently outward through the space surrounding the binary. In the infrared image, they appear as a nest of concentric curves, a structure so geometrically precise and so unexpected that it has the look of something drawn deliberately, though nothing in it holds any intention at all. It is only orbital mechanics and thermodynamics playing out across the slow time of stellar evolution, leaving a visible record in condensed solid matter. Those dust rings are not permanent. As they expand and the radiation field around them thins with distance, they become increasingly tenuous. The individual grains spread more and more thinly across a growing shell surface. Eventually, they will disperse entirely into the surrounding interstellar medium, the carbon atoms from each ring joining the general pool of enriched material that Wolf-Rayet stars contribute to the galaxy throughout their brief lives. Long before any ring disperses, the binary system will have moved on, the stars continuing their orbit, the next periastron coming, the next ring forming, and then beyond that, in a time that is still distant, but fixed by the physics of what these stars are, one or both of them will die. The death of a Wolf-Rayet star is the death of one of the most massive objects that can exist. By the time it arrives, the star has already shed enormous quantities of mass into the surrounding space. A Wolf-Rayet star that began its life with 60 or more solar masses of hydrogen and helium and trace metals may have lost 20, 30, or more solar masses to its wind, and in binary systems, to mass transfer. What remains at the moment of death is a compact, stripped core, primarily helium, with a deep interior of carbon and oxygen from the triple alpha process, and at the very center a shell of silicone and a growing core of iron that is the end product of all the nuclear burning sequences the star has passed through. Iron is where fusion ends. Every element lighter than iron releases energy when nuclei fuse together. Iron does not. To build nuclei heavier than iron requires an input of energy rather than a release of it. And so when the central core of a massive star reaches iron, the fusion that has supported the star against gravity for millions of years reaches its terminus. The iron core simply accumulates, growing with each shell burning event above it until it reaches a critical mass. At that point, in less time than it takes to breathe, the core collapses. The collapse falls inward at a quarter of the speed of light. A core that was thousands of kilometers across shrinks to a sphere of roughly 20 kilometers in less than a second. The density it reaches exceeds that of an atomic nucleus, matter compressed until electrons and protons are forced together into neutrons, until the quantum pressure of those neutrons is all that remains to halt the contraction. If the core is massive enough, even neutron degeneracy pressure is insufficient, and the collapse continues past the neutron star state into a black hole without any halting bounce at all. The outer layers of the star, still falling inward at the moment of core collapse, encounter either the rebounding shock from a neutron star formation, or simply continue to fall when no such bounce occurs. What escapes and what falls back depends on the mass of the collapsing core, on the rotation of the star, on the properties of the surrounding envelope, and on processes in the innermost regions that remain among the most actively studied in all of high-energy astrophysics. For stripped envelope Wolf-Rayet progenitors, stars that have already lost their hydrogen and often their helium as well, the observable outcome at the stellar surface is a core collapse supernova without hydrogen lines in its spectrum. A supernova with no hydrogen lines is classified as type Ib if helium remains, or type IC if even the helium has been removed. The absence of hydrogen in these transient spectra is the direct observational signature of the stripping that defined the progenitor star's final evolutionary state. The spectral classification of the death carries the record of the life. The rate at which stripped envelope supernovae occur across the local universe is roughly consistent when binary progenitor channels are included alongside single-star wind stripping, with the number of Wolf-Rayet stars that can be expected to die within any given volume of galaxy over the same period. The accounting is imperfect. Massive stars are rare, and the nearest Wolf-Rayet stars are still hundreds of light years away, close enough to observe in detail, but far too distant for the death of any one of them to represent an event a human lifetime is likely to encompass. Still, the population-level agreement between Wolf-Rayet death rates and stripped envelope supernova rates supports the identification. These are the stars whose deaths, from Earth's distance, look like the most extreme optical and X-ray transients in the observable sky. Some Wolf-Rayet deaths are more extreme still. A Wolf-Rayet star that reaches iron core collapse with high angular momentum, rotation fast enough that the collapsing material carries significant spin, may not simply form a neutron star or an undifferentiated black hole surrounded by infalling debris. Instead, the collapse produces a black hole surrounded by a thick, rapidly rotating disk of material, accreting onto the new object at rates of a small fraction to a full solar mass per second. At those accretion rates, the energy liberated from the disk is enormous, and some fraction of it is channeled into two narrow jets of plasma, moving outward at close to the speed of light, directed along the rotation axis of the collapsing star. Those jets drive outward through the still collapsing envelope, pushing through the carbon and oxygen and silicone shells above the iron core, drilling through layers that were once the interior of a star that had been burning for millions of years. The material around the jet is compressed and heated, forming a hot cocoon that may be bright in X-rays. If the jet is energetic enough and the stellar envelope thin enough, conditions more readily met in low metallicity stars, whose winds did not slow the core's spin, the jet punches out through the surface and into the surrounding space. There, the relativistic outflow interacts with the interstellar medium, producing a burst of gamma rays lasting from seconds to minutes or longer, followed by a longer-lived afterglow as the jet decelerates. These are long-duration gamma-ray bursts, and the progenitor model that best accounts for their properties, the distribution of their energies, their association with galaxies of low heavy element content, their connection to type IC supernovae without broad hydrogen or helium features, centers on exactly this kind of rapidly rotating, stripped envelope Wolf-Rayet progenitor. The detection of a gamma-ray burst means that somewhere in the universe, at the distance its redshift implies, a Wolf-Rayet star has just completed its life in the most energetic way available to a massive stellar object. The energy released in the burst alone, if isotropic, would exceed the total light output of billions of ordinary stars. It is not isotropic. The jets are narrow, and the apparent brightness reflects the collimation of the energy into a small solid angle. But even accounting for the geometry, the luminosities involved exceed by orders of magnitude what any non-relativistic event can produce. And the conditions that produce them, high rotation, low metallicity, stripped envelope, describe exactly the evolutionary endpoint of a Wolf-Rayet star in a metal-poor environment, where its wind was never strong enough to spin the core down or to carry away enough mass to prevent the formation of a rapidly rotating iron core at the end. The preference of long-duration gamma-ray bursts for low metallicity host galaxies is one of the cleaner observational constraints in the field. Metal-rich stars lose more mass and more angular momentum to their winds. Metal-poor stars, in galaxies where the abundance of elements heavier than hydrogen and helium is lower than in the Milky Way, retain more of their spin. The difference in final core rotation between a metal-rich Wolf-Rayet dying in the inner Milky Way and a metal-poor Wolf-Rayet in a small, chemically unevolved dwarf galaxy may determine whether the death is a relatively quiet, stripped envelope supernova or an event visible across most of the observable universe. The star does not know the difference. The outcome is written in the initial conditions of where and when it formed. Where a Wolf-Rayet star leaves behind not a black hole, but a neutron star, when the core mass is lower and the collapse is survivable in the neutron star sense, the remnant spins rapidly, magnetized, and may become a pulsar. Pulsars from stripped envelope supernova progenitors are expected to be born spinning faster on average than those from hydrogen-rich progenitors, because the stripping of outer layers concentrates the core's angular momentum rather than distributing it through a large, slowly rotating envelope. The fastest spinning neutron stars, the millisecond pulsars, have typically been spun up later by accretion from a binary companion, but the connection between Wolf-Rayet progenitors and the initial spin distribution of neutron stars in binary systems is a thread running through multiple lines of observation. Black holes left by Wolf-Rayet collapse carry the mass of stripped cores, lighter than the most naive estimates because of all the mass the star shed before it died, but still substantial. A Wolf-Rayet star that began its life with 40 or 50 solar masses and shed the majority of its envelope through winds and binary interaction may leave a black hole of 5 to 20 solar masses, sometimes more at low metallicity. These black holes are stellar mass objects formed in isolation or in binaries, and in binaries they may be paired with the companion that helped strip them in the first place. When two such black holes exist in a binary system, each the remnant of a Wolf-Rayet star that lived and stripped and died, they orbit each other as the binary loses energy, slowly at first and then faster as that energy escapes in the form of gravitational waves. Gravitational waves are distortions in the fabric of spacetime itself, propagating outward from any mass that accelerates, but detectable only when the masses involved are large and the accelerations extreme. A pair of stellar mass black holes spiraling inward through their final orbits satisfies both conditions. As they approach, the orbital frequency rises, the amplitude of the gravitational waves increases, and in the final fraction of a second before they merge, the signal sweeps upward in frequency and intensity before cutting off as the two holes become one. On September 14, 2015, that signal reached Earth. Two gravitational wave detectors, their arms kilometers long, and their mirrors exquisitely isolated from every terrestrial vibration, registered a distortion in spacetime passing through the planet at the speed of light. The signal lasted less than a second from detection to merger. Analysis of the waveform, the specific way the signal's frequency and amplitude evolved through that fraction of a second, revealed the masses of the merging objects, one of approximately 29 solar masses and one of approximately 36, producing a final merged object of around 62 solar masses, the remaining mass having been converted to gravitational radiation and radiated away. Both component masses fall within the range expected for black holes formed by Wolf-Rayet progenitors at low metallicity. The distance to this merger was roughly 3 billion light-years. The merger itself occurred when multicellular life on Earth was still young. The signal it sent traveled through expanding space for over 1 billion years before the detectors existed to receive it, before the understanding existed to interpret it, before the stars whose deaths gave rise to those black holes had been classified and studied and fit into an evolutionary sequence by patient observers over more than a century of accumulated spectroscopy. All of that time, the signal was traveling. The space it moved through changed. Galaxies that had once been close to the source of the merger drifted apart. New generations of stars formed and completed their lives in the Milky Way, and the wave arrived. The first detection established that stellar mass black hole binaries exist and merge, that gravitational waves carry real energy and warp real spacetime, and that the universe contains objects in the mass range that Wolf-Rayet evolutionary models had predicted. Subsequent detections in the years that followed filled in a distribution of merger masses and mass ratios, some consistent with Wolf-Rayet progenitors at various metallicities, some pointing to other formation channels. The field is still being written. Each detection adds 1 point to a distribution that will eventually, with enough events, distinguish cleanly between formation pathways. For now, the connection between Wolf-Rayet stars and the gravitational wave events recorded on Earth is not a certainty for any individual detection, but a statistical likelihood across the growing population of observed mergers, and a theoretical expectation grounded in a century and a half of stellar physics. The carbon and nitrogen and oxygen that a Wolf-Rayet star exhaled during its lifetime are already in the interstellar medium before any of this happens. The wind does not wait for the supernova. For hundreds of thousands of years before the iron core collapses, the star has been moving through space with its wind spreading outward in all directions, enriching the surrounding gas with the products of nuclear burning, contributing to the chemical budget of the molecular cloud or the galactic disk where it resides. By the time the end comes, the material nearest the star, the slow-moving swept-up shell of a ring nebula, the faster-moving inner wind, the shock-heated interface where the wind meets the interstellar medium, has been in motion for so long that it is already scattered across volumes of space spanning many light years. The supernova, when it arrives, adds to this. The explosion ejects the remaining mass of the stellar layers that were not incorporated into the central remnant, sending carbon and oxygen and silicon and the iron group elements synthesized in the final burning phases outward at velocities of thousands of kilometers per second. In the centuries and millennia after the explosion, the supernova remnant expands, sweeping up interstellar gas, decelerating, mixing. Eventually, the remnant structure dissolves into the general interstellar medium, its material indistinguishable from the ambient gas that surrounds it. Somewhere in that mixed medium, drifting through molecular clouds and the warm ionized phases of the galaxy, are the atoms that were once inside a Wolf-Rayet star. Some of those atoms will eventually be incorporated into new stars. The slow cooling and gravitational collapse of enriched molecular clouds leads to new generations of stellar objects formed from gas that is chemically more complex than the gas that formed the generation before. Each cycle of massive star formation, evolution, and death, each passage of material through the hot compressed interior of a massive star and back out through its wind or its supernova, raises the metal abundance of the galaxy's star-forming gas by a small increment. Wolf-Rayet stars are among the primary contributors to this enrichment at the high-mass end of stellar evolution, because their winds are so strong and their lifetime so brief that they return their processed material quickly, on timescales that are short, even compared to the orbital periods of giant molecular clouds. In the atoms of the surrounding gas, there are now records of the temperatures and pressures that prevailed inside these stars. The carbon isotopes carried in a Wolf-Rayet wind bear the mark of the triple alpha process that made them. The nitrogen isotopes carry the mark of the CNO cycle. The oxygen, the neon, the trace heavy elements carried out in later burning phases, each carries some signature of the interior conditions from which it emerged. These chemical records are not easily read, and much of the detail is erased by mixing and reprocessing as material cycles through the interstellar medium. But in a general sense, the gas from which new stars form is shaped by all the stars that have already lived and died in the same region of the galaxy. The molecular cloud that will one day form new stars, including perhaps stars massive enough to begin the same evolutionary sequence again, is already turning slowly. It has been turning since the angular momentum of the broader galactic disk was imprinted on it. Inside it, regions of slightly higher density accrete more gas under gravity, growing denser still in a process that moves slowly at first and then accelerates as the local freefall time shortens. From those density peaks, over timescales of millions of years, cores form. The cores fragment. Protostars ignite within the fragments, and among the new stars that emerge from the cloud, some will be massive enough, 20, 40, 60 solar masses or more, to pass through the same arc of hydrogen burning and envelope stripping that defines the Wolf-Rayet evolutionary pathway. Those future stars have not yet formed. The gas from which they will coalesce is drifting through the present galaxy, cooling and turbulent, and seeded with the chemical output of all previous stellar generations. Among that gas are atoms that pass through Wolf-Rayet interiors, through the fierce winds and the ring nebulae and the supernova remnants that concluded those stars' lives. The atoms do not carry any memory of this passage. They carry only their nuclear structure, the particular configuration of protons and neutrons that determines what element they are, a configuration set by the nuclear reactions that made them and unchanged by every subsequent event. When they eventually join a new stellar core and begin to be processed again, they will behave as they always have, fusing or capturing or decaying according to the conditions around them, contributing their small increment to whatever the new star ultimately makes. This is the character of the galaxy's chemical evolution, not a single arc moving in one direction, but a cycle recurring across time, each iteration beginning with gas that is slightly more enriched than the gas of the iteration before. The most massive stars complete their contribution to this cycle in only a few million years. They arrive quickly from molecular cloud collapse, burn briefly and intensely, shed their outer layers in winds that enrich the surrounding medium, and then die in events that add still more material to the general interstellar pool. Their brevity is inseparable from their contribution. A star that burns for 10 billion years, as the sun will, processes its interior material slowly and returns it only at the very end in a planetary nebula. A Wolf-Rayet star returns material continuously throughout its brief life, and then returns more at death. There is something in this that the word end does not quite capture. The Wolf-Rayet phase itself, the brief, hot, stripped, intensely radiating phase between the main sequence and the supernova, is already near the end of a sequence that began millions of years earlier, when a dense core in a molecular cloud first contracted under its own weight. By the time a star becomes a Wolf-Rayet object, it has already completed the longest part of its life. What remains is geologically brief, cosmically brief, and spent in the most extreme physical conditions the star will ever occupy. The wind is at its most powerful. The surface is at its hottest. The luminosity is near its peak. The rate of mass loss is at its highest. And all of it is moving, in the language of stellar physics, toward the iron core that will form last and collapse first. At the moment of collapse, the outer layers are still in motion. The wind is still flowing outward. The ring nebula that the wind carved earlier is still expanding, somewhere beyond the reach of the blast. The companion star, if there is one, is still in its orbit, moving around a center of mass that is about to change abruptly as the primary loses most of its mass in the supernova explosion. The dust shells of previous periastron passages in a system like WA 140 are still drifting outward at wind velocities, moving calmly through the space surrounding the binary, unaware, in the only sense that word can mean for condensed carbon grains, of what has happened at their source. The light from the supernova will take years to reach the outermost dust shells. In that interval, those shells continue their expansion, carrying their carbon outward through a space that has just been vacated by the star that made them. When the light finally arrives, the ultraviolet and optical flash of the explosion, followed by the slower cooling optical display of the supernova remnant, the dust grains will be exposed to a brief, intense pulse of radiation, very different from the steady wind that formed them. Some may be sputtered away, some may survive, incorporated into the expanding supernova remnant shell. Either way, their material eventually enters the same general interstellar medium that receives all the other ejecta, and the distinction between material shed by the wind during the star's life and material ejected by the explosion at its death gradually becomes irrelevant. The galaxy does not distinguish between these contributions. Its chemistry accumulates them without record. The carbon from the wind and the carbon from the explosion diffuse into the same molecular clouds and eventually into the same new stars and the same planetary systems. In those systems, some carbon will end up in the mantles of rocky planets, or in the crusts of ice-covered moons, or dissolved in subsurface oceans warmed by tidal forces from a nearby gas giant. Some will drift through interplanetary space as part of the dust that fills every solar system. Some, in circumstances that require no special conditions beyond time and chemistry, may be incorporated into organic molecules complex enough to be worth studying in their own right. None of this needs to be thought of as directed. The carbon did not intend any of these destinations. The Wolf-Rayet star that made it did not intend to make it. The nuclear physics that converted 3 helium nuclei into a carbon-12 nucleus in the star's helium-burning interior followed no plan, only the thermodynamic conditions prevailing in a hot, dense core. Yet the outcome of all these undirected processes, accumulated across billions of years of galactic evolution, is a universe in which the material formed inside massive stars moves through interstellar space and finds its way into new structures, new systems, new arrangements of matter that could not have existed before the stars made their contributions. The Wolf-Rayet stars in the Milky Way tonight, the several hundred confirmed objects, the additional population suspected to lie beyond dust clouds in the inner galaxy, the distant counterparts in galaxies hundreds of millions of light years away, observed only as points of spectroscopic light, are all at different stages of the same arc. Some are freshly arrived at the Wolf-Rayet stage, still carrying traces of hydrogen in their outermost layers, their WN spectra showing the nitrogen and helium of CNO cycle products just beginning to be exposed. Some are deeply evolved, their surfaces showing the carbon and oxygen of the WC stage, their hydrogen envelopes entirely gone, their cores burning helium, or the products of helium burning in the inner shells, while the outer layers blow away at velocities the human body cannot readily hold in mind. Some have a companion star moving in a slow or rapid orbit around them, the orbital configuration shaping the wind interaction, the dust formation, the eventual mass transfer if the companion itself is still on the main sequence, and the Wolf-Rayet star evolves faster. Some are alone, their stripping accomplished entirely by their own radiation and their own wind, no companion to complicate or alter the arc. Each one is moving toward the same terminus at its own pace, shaped by its own initial mass and metallicity and rotation and orbital history. None of them will wait long in the timescales of the galaxy. The most massive and luminous will exhaust their remaining fuel in 100,000 years or less. The least extreme Wolf-Rayet objects may persist in this phase for several 100,000 years. Against the background of galactic time, these are moments, brief occupancies of a particular evolutionary state, followed by the quiet discontinuity of core collapse. And beyond that discontinuity, the material continues. The black hole or neutron star at the center carries forward the angular momentum and the remnant mass. The ejecta carry forward the chemical enrichment. The gravitational wave signal, if the collapse is energetic enough and the geometry favorable, carries forward a distortion of spacetime, propagating outward at the speed of light, detectable in principle anywhere in the universe with a sufficiently sensitive instrument, a record of the moment of collapse encoded in the fabric of space itself and moving outward through it, long after the star that sent it has been entirely transformed. On the ground, under a clear sky, the stars in Cygnus appear fixed. The constellation has the same shape it had last night, and the same shape it will have 1,000 years from now. Against the span of human memory, the sky is static, the stars unchanging, the same patterns rotating overhead in the same slow cadence they have always observed. In this stillness, the Wolf-Rayet stars are invisible to the naked eye, too distant, their optical light diluted across too great a gap of space, and the work they are doing in their bright, fierce, brief lives is not announced by any change visible from here. The winds are flowing, the ring nebulae are expanding. In some of these stars, the iron core is already forming, shell by shell, neutron by neutron, a process that began long before this night and will continue long after. The carbon rings of WR 140 are moving outward through the infrared dark, expanding at wind velocities into the surrounding space, each one a quiet record of a close passage that happened years or decades or centuries before the humans who would eventually image them were born. The gravitational waves from mergers of black holes that were once massive stars continue to pass through the Earth without announcement, too faint by many orders of magnitude for the detectors that register the strongest events to register these. The accumulated background of all the binary mergers happening across all the galaxies in the observable universe at any given moment, washing through the planet as a continuous unresolved hum of space-time curvature too quiet to be heard. And in the molecular clouds of the Milky Way, where the density is highest and the temperature has fallen to within tens of degrees of absolute cold, the gas that will form the next generation of massive stars is drifting and accumulating, turbulent and slow, seeded with carbon and nitrogen and oxygen from all the Wolf-Rayet stars that have already completed their arc. The atoms wait in that cold. They have no memory of where they have been. They do not know that they have been inside a star, that they passed through a wind moving at thousands of kilometers per second, that they were once part of a ring nebula glowing faintly in hydrogen light against the dark. They are simply matter resting in the cold interstellar medium, carried along by the slow gravitational currents of the galaxy, waiting, in the only sense that word applies to matter without mind, for the density to rise enough, the temperature to fall enough, the local turbulence to quiet enough, for the long collapse toward a new stellar core to begin. All of this is happening. It is happening at distances that light measures in thousands of years, in timescales that geology measures in millions. From a dark room, from the stillness of this hour, It is the same sky as always, old and quiet and deep, holding its brief, hot, stripped, luminous stars in the same patient dark it has always held them in, the same dark it will hold them in long after this night, and all the nights that follow it, have been gathered into the slow drift of accumulated time and set aside